Yeah, colleagues, so let's start our last day of conference Nano 2025. And now we have section Nanochemistry and Nanobiotechnology. And the first speaker, Professor Sergei Kurta from Vasil Stefanik Petropassian National University.
Thank you very much. I'm very glad to see you in our conference. And I'm very congratulations to the participants of the international conference, Nanotechnology and Nanomaterials 2025. I'm coming to the from the Department of Chemistry with the Carpathian University in Ivan. Okay, let me start. Let me present our research, the chemistry and the technology of extraction of the natural isoprene squalene oligomer from the amaranth oil. On the first slide, we can see the chemical formula, the squalene, and the amaranth. In amaranth oil, we use the squalene is a very interesting substance. And this slide, we can see the preparat for the squalene, the Japanese drug capsule squalene on the first page. On the 2 page, we can see US drug squalene oil product in the United States. This is preparat is very interesting, and there preparat we use for our life. Okay. On this slide, we can see the formula of squalene, C30 and H50, and the hexamethyl tetrahydrogen. And the squalene, this is squalene. This is unsaturation squalene and squalene saturation hexamethyl tetrahydrogen. And there is properties of the squalene on this you can see, and properties for the squalene. Squalene in this saturation form of squalene is very interesting. Squalene produced for the sharp oil. You can see on this page, and squalene can contain and sharp oils in 1-2%. But we and me produce the squalene, the amaranth oil. You can see on this page. But the content the squalene of amaranth oil is a 6 or 9%. Okay, and this year we can growth of amaranth of this page we can see on our square in the university in the Ivano-Frankivsk, nearly the about the town. And we produce the squalene of our laboratory. You can see on this on this page. The chemical content, the chemical composition of squalane, we can see of this table. We can see this some linoleic acid, linolenic acid, oleinic acid, palmithenic acid, and stearinic acid. And the main of the substances for the knife, for the ours, is the squalane, the hexaoligomer of isoprene. The content of the oil we obtain of 6 or 8%. On this slide, we can see this icosane pentanonic acid and decosane hexanonic acid and alpha-linoleic acid, the content of the oil in squalane. Amaranth grain in oil is very rich sources for the vegetable proteins and unsaturated fatty acid. It is the use of the several amount of the also made the very valuable of obtain. Okay. The squalane is very interesting substance by the product of our body. On the figure number 11, we can see the product of squalane of our skin, of our people's skin. And squalane products of the epidermis of our skin and contain of surface of our skin and polymerization of our skin and protect of our skin after time. The very interesting substances, the very interesting properties of squalane is the polymerization in the content the peroxide water and water. Of reaction number 3 and number 4, we can see how squalane react of the water and obtains the squalane. Squalane obtains the squalane. 6 molecules of water we obtain of squalane. And squalane added to 6 molecules of peroxide water, we obtain of squalane. This reaction it consists in the our square of our skin. We obtain is very interesting protect of our skin. This the figure number 11. We can see the formula of squalane. Okay. The squalane is a very interesting substances in the medical center in the University of Kansas City. Showed that after the 1 month molecule with the first group of moles, which was exposed of radioactive irradiation and thus of which a small rodent was lethal and amounting to the 100%. And most from the set group each received of squalane during the entire period experiment remained alive and deposited in various deposits from the large area. The squalane is very, very protective substances for our life. On other slide, we can see the amaranth in Ukraine, translating the on the with amaranth oil for the seed of the squalane on the figure number 4. At the chemistry department of the faculty of the natural science of the Basil Stefanik Department University in one of Frankfurt, we conducted applied studies with various technological methods, the separation and deparaffinizations squalane and squalane from amaranth. On this page, we can see the amaranth or amaranth of our country. There we obtain the amaranth oil or the associating of amaranth and amaranth product products under the management by Dr. Alexander Duda. And we can see of this page. Okay. As a result of the research conducted by scientists from the Department of Chemistry of the mine, we registered of the produced by patent Ukraine number method for the removing squalane and squalane from the oil as pre-active. The new simplified method for the detecting of squalane and squalane from amaranth oil from laboratory produced and present of the number 7, 8, and 6. In this year, we patented the 2 patents of our squalane number. We can see this precipitating only unsaturation squalane, carbon 30 and hydrogen 50, and the unsaturation is saturation squalane, carbon 30 and hydrogen 64 from the amaranth oil. And as a result of the experiment, we provided of the sterilization method for the obtain of squalane. On the table numbers 3, we can see the properties of squalane. In this color, the yellow, you can see of this page, with the component and the peroxide number and the density. And then on this slide, we can see the squalane after the sensitivity. Okay. In the future, we isolate the squalane and squalane from the input amaranth oil if produced by the Ukrainian amaranth oil from the Nanomaterials in Ukraine. We represent of the ceramic special of shaped amaranth special product in the Alexander Duda. And presented of the customer and analysis of the characteristic presented of the table. The very interesting properties of squalane is the density, but after the depolymerization, we can see the density on 0.930. After the deparaffinication, we can see the 50 gram of the centimeter where it's setting. In the very, very small, very small difference of other before and after depolymerization. This is very nearly the substances of the squalane and squalane. This table, we can see the refraction indication of the simple squalane, and we can see this the difference is very, very small. This is this substances we can obtain. For the on this table or substances we can point it of our work, we can see we can take of the plant derived squalane made in the star we can see the sharp squalane from the Norwegia and made in Praga, and the 40 and 50% contained in squalane. And we can see this so very small difference of our well, and in this slide, we can see the infrared spectral analysis of amaranth simple, the squalane and squalane, and we can see this lead simple amaranths. We can see the decreases absorption and the region of 2095 centimeters and the 2048 centimeters. And this centimeter is very different, but the squalane is saturation, squalane and saturation. Okay, on this slide, we can see the difference in thermal analysis, sample the amaranth oil and squalane. And we can see that this indicates the great resistant thermal decomposition amaranth oil number 1 and 4 compared to the ordinarily 100 squalane standard. But our squalane we can obtain with very thermal stability, very thermal stability. Okay, and the some sample of our oil, amaranth oil, we analysis of the LMD mass spectrometry method, and the table interpretate of this global. We can see this our method is very interesting, but in the difference of squalane and squalane in our sample. And liquid chromatography analysis was made of this page, and amaranth and squalane oil, and very different for some very interesting. Okay, and on this slide, we can see this our simple preparation of the squalane and squalane. For example, figure number 17, we can see the detailed anti-stress theorem for the Hessian stein with the contains 3 or 5 natural squalane. And figure number 18, we can see the cosmetic oil for the baseboard. And on the figure number 19, we can see the high Guinea leaf trick for the amaranth oil. And the last page, we can see number 20, the strong proem that contain 40 or 20 squalane and squalane. We produced of this proem on our department in the chemistry in the Carpat Nation University. Okay, this is conclusion of our presentation, and the new is that the application registration the patent of Ukraine. The one patent is the method obtained the squalane and squalane from the animal fats, and 2 patent we obtained the cosmetic composition for the natural squalane in composition properties for the green and natural squalane. This patent we obtained of our. This is reference You can see publication of our work, and there's red. You can see there's our patent and our publication. And thank you for your attention to our presentation. And I am looking forward for the question. Since are you? Last slide, we can see the protection cream we produce of our department, and this cream I can present of our conference, and we can buy of the cream and we can try of our skin. Thank you very much, and I listen with pleasure.
Thank you for your presentation.
Крем я привіз відповідно до цього, бо нам був на минулій конференції, де сидять в ми ще не купували, а зараз ми маємо крем, і це повні чином. Це така річ, яка жінки від нього мріють. Значить, далі він відтворює якість поверхні шкіри, ну, робить вас молодою. Це приємно. На декілька років то це не вийде, а от на декілька годин це... Ну, але це нормально, це і так треба десь піти до когось, з кимось зустрітися, вже молоді, і вам нічого не бракує. Дякую. Він перевірений, відповідно, він пройшов. Сертифікацію ще не пройшов, тому що ми тільки в цьому році, відповідно, навчилися його робити, але він пройшов медичне випробування. Тут 4 компоненти. Тобто сам скваленова, відповідно, олія, є ще згущаючий засіб, ми використовуємо природні жири, і тому тут нічого немає. Ну і як загущувач ми використовуємо. Тому тут всі натуральні компоненти, нічого хімічного немає. 4 компоненти з тих, що виробляються в природі, ви можете їх спробувати. Дуже допомагає.
Thank you for your interesting presentation. Unfortunately, we have no time for question, and we go to the next speaker. The next speaker will be Dr. Oksana Balaban from Lviv Polytechnic National University.
Hello, everyone.
Hello.
Thank you for kind introduction. Today's my topic is synthesis and energy storage properties of inorganic organic composites for lithium-ion batteries for cathode materials. Our team today consists of chemists responsible for synthesis of composites and physics responsible for energy storage properties checking. This content is for today consists of 4 parts that will answer the question, why did we choose this topic, what materials and how we produce them, what results did we obtain, will they be useful, and who might be interested in these results. First of all, I would like to speak about our research laboratory of nanophysics and molecular energy engineering. In our laboratory at the Department of Applied Physics and Nanomaterials Science, we carry out investigation of materials, synthesis, and also different type of modification of materials for energy storage devices and micro-nanoelectronics. Speaking about micro-nanoelectronics, we check the different phenomena, for example, magnetocapacitance, spin batteries phenomena, magneto-resistance phenomena in semiconductor materials, and their sensor properties under different external fields, physical fields. Speaking about energy storage devices, we check and also investigate materials, natural materials, and synthesized materials for lithium batteries and supercapacitors. And today I'll speak about this part of our investigation. Why did we choose this topic? Honestly, is the integration of renewable energy sources, for example, solar sources or wind sources, has intensified the need of storage materials. Yes, from the other hand, there are a lot of different portable devices, starting from electric watches, yes, or smartphones, or electric vehicles, and also drones. And all of them need powerful batteries that will be efficient and has a long-term cycling. Yes, that's why we need new materials or a different type of modification of market materials to obtain high energy capacity of batteries. Yes, there are various of types of batteries on market, and each of them, for example, lead acid, yes, has its own advantages. For example, or cost or fast charge. But as you see here, lithium-ion batteries have more advantages than others. For example, high specific energy, operating voltage, cycling life, fast charge, and low toxicity. But these advantages are not enough today for application in portable electronic devices in modern world, yes, and with technological progress. That's why we carried out investigation of materials for lithium-ion batteries. The characteristic of lithium current sources depend on the diffusion rate of lithium ions, high ionic conductivity of materials, also chemical and electrochemical stability, possibility of intercalation and deintercalation of large amount of lithium ions, and also structure of cathode materials. Usually, the materials for lithium-ion batteries have such layered structures, and molybdenum disulfide is one among them. From the other hand, polymeric materials today have a lot of application. For example, biomedical application, food packaging, electronics, and energy storage. That's why in this research, we proposed to combine these inorganic materials with these organic polymers to obtain higher specific capacity, low resistance, and high diffusion of lithium ions. Previously, we carried out investigation with both of them, but in today's topic, I'd like to tell about one more modification. That's why here we obtain core shell nanoparticles via these 4 steps. And in the first step, we perform sorption modification of silicon dioxide porous materials with average diameter of 27 nanometers and average pore size 10 nanometers. We produce sorption modification with uptest. Uptest plays a role of clay that is necessary for our next step. So secondly, via hydrothermal synthesis, we obtained molybdenum disulfide nanoparticles inside of these silicon dioxide pores. And third and fourth stage is necessary for a further modification that calls grafting from method, grafting polymerization of 2 different types of polymers. That's why here I sum up our 3 materials that we have investigated. So pristine one, core shell, molybdenum disulfide, and silicon dioxide nanoparticles, and covered by fast polymer. This is the type of polymer, thickness of polymer, and content of polymer on the surface of this core shell composite. And the set one with double polymeric shell. Yes, we add polydimer here, and the total thickness is 82.5 angstroms. By the way, we produce synthesized nanoparticles, composites, yes, with and without uptest. But as a result, we obtained here, without uptest, yes, we obtained here nanoparticles molybdenum disulfide not inside the pores of silicon dioxide, but only after using uptest, we obtained such core shell nanoparticles where molybdenum disulfide are inside silicon dioxide pores. Speaking about energy properties of our materials, we obtained such discharge covers of our three materials. And what is interesting here? The interesting here is appearance of such platos. These platos mean that we have two fast states here and also phase transition that correspond to possibility of recharge our materials. The obtained values of specific capacity in comparison with literature data are presented here. First three materials is our materials, yes, and here is literature data. As you can see, this second line, yes, our materials have a higher specific capacity. This is due to this only one polymeric shell. The next step is investigation of kinetic parameters of lithium intercalation process. And of this results were obtained via impedance spectroscopy presented by Nyquist diagrams for our three materials. The shape of this cover of these photographs consists of these semicycles and a low frequency tail. This tail corresponds to diffusion. So this generally view for lithium-ion batteries. Yes, the corresponding electric circuit that we use to simulate experimental results is present here and consists of electrolyte resistance, two parallel links, RC links that correspond to interlayer barriers and also polymeric shell. And this one is a Randall-Ashler scheme, consists of double layer capacitance or Helmholtz capacity, also RKT current transition resistance, and here is Warburg element that is Warburg impedance correspond to diffusion of lithium ions. Results of simulation are presented here by lines. Symbols experimental results and lines are simulation results. They coincide well and the accuracy did not exceed 5%. Results of simulation of Randall-Ashler part of the scheme is presented here, and we obtained the charge transfer resistance, high values for materials with polymeric shell, one or double polymeric shell, and low resistance for our pristine core shell inorganic nanoparticles. The highest value here is we can explain by dielectric polymeric shell here. Yes, that's why charge transfer resistance increase. This. Speaking about Helmholtz capacity, we obtain a higher value for polymeric coated materials and a bit lower value for pristine core shell nanoparticles. By the way, these Helmholtz capacity values are necessary for application of lithium-ion batteries in impulse mode. Speaking about lithium-ion diffusion coefficient, unfortunately, we obtained lower value for materials with double polymeric shell. We can assume that these values are lower because of thicker polymeric shell. And for first and second materials, they are pretty the same. Values of lithium diffusion coefficient are pretty the same. The correspondence and literature data of lithium diffusion coefficients are presented here, and here is other values, and here from literature data information. So one can see that we obtain a bit less values. So our next step will be to produce another type of modification, probably use another types of polymers to vary with thick of these polymers, yes, to obtain higher values of diffusion. But at all, you can find out that we obtain advantages in specific capacity values here, yes? And in conclusion, I just wanted to say that we obtained core shell nanoparticles via hydrothermal synthesis and high specific value capacities. And our next step will be another modification to obtain lower resistance and higher values of diffusion coefficient of lithium ions. And thank you for your attention.
Thank you for your report. Maybe somebody have questions. Questions. Thank you again. We will move forward. Our next speaker, teacher student, Julia Frisch.
Yes, I'm here. Good morning.
Hello.
Please
Do
take
you
your
hear me
floor.
well?
Yeah, open the presentation, please.
One moment. Okay, so is it visible?
Yeah,
Do you see presentation?
yes, please take your floor.
Okay, thank you. So good morning to all conference participants, and it's a pleasure to have the opportunity to present the result of our research here today. Graphene oxide nanoparticles have unique properties and are widely used in various fields, including biology and medicine. So these nanoparticles, however, also exhibit toxic effects, and therefore the understanding the molecular mechanism of graphene oxide toxicity is very important, mainly for the nanomedicine, especially the cancer therapy. That's why the aimed That's why the study aimed to examine the impact of graphene oxide nanoparticles on the expression of genes associated with endoplasmic reticulum stress, proliferation, and cancerogenesis in normal human astrocytes and glioblastoma cells. Each gene that we studied play important role in proliferation and in growth cells, and all these genes are stress dependent, endoplasmic reticulum stress dependent. For conducting this research, we use methods and materials that are described on this slide. And the main idea is that we impact normal human astrocytes align NHTC or Tanaka-Sasai, and you AT7MG glioblastoma cells, stable, transfected by empty vector or DNA ER1. It's a third line cell. Were exposed to low doses of graphene oxide nanoparticles in dose 1 and 4 nanogram on milliliter for 24 hours. On this slide, you can see that a relative expression of one of important genes that involved in adipogenesis and erythropoiesis, and it's activated by endoplasmic reticulum stress and promotes apoptosis. So we see that graphene oxide increased relative expression of the gene in normal human astrocytes more than in glioma cells. On this slide, you can see that the same changes, but for another gene that is co-chaperone for protein HACPA5, which acts as key repressor for ER1-mediated unfolded protein response. And as we see, changes are more increased in normal human astrocytes than in glioblastoma cells. On this slide, it's shown that relative expression of EDM1 is increased in dose-dependent manner, mediated by graphene oxide in normal human astrocytes more than in glioma cells, and this protein is important for misfolded protein binding activity, and this protein touched into the endoplasmic reticulum and proteolysis. On this slide, you can see the key regulator of unfolded protein response, ATF3, or activating transcription factor 3. And we see that graphene oxide increased the relative expression level of this gene in normal human astrocytes more than in glioma cells. Some the same changes is described on this slide for ATF4 for another gene that too is important for for protein-protein interaction, and it play important role in PERK analysis, PERK pathways. So on this slide, we described that relative expression of TOP1 increased too, mediated by graphene oxides in dose-dependent manner, and for 4 nanogram on milliliter, this relative expression decreased more than for glioma cells. This protein is a member of the family of anti-proliferative protein, and it can regulate the cell growth. And another changes we fixed for this important enzyme, IDH2, and it's important in anti-proliferative interaction, and we see that relative level of expression of the gene is decreased, and it changes in comparison of glioma cells that in the but for glioma cells the changes were minimal. Maybe it can be because of resistance glioma cells to different influence. So in result, we showed that treatment of normal human astrocytes and glioblastoma cells by relatively small doses of graphene oxide nanoparticles affected the expression level of DDIT3, DNAGB9, ADAM1, ATF3, ATF4, TOR1, and IDH2 mRNA, but the sensitivity of all studied mRNA expression to these nanoparticles was significantly higher in normal astrocytes than in glioblastoma cells. And I should mention that minimal changes in gene expression are mediated by we studied also glioma cells with suppressed ER1 activities, and minimal changes in gene expression are mediated by suppressed of activity of ER1 endoplasmic reticulum main gene. So in conclusion, the data obtained demonstrate that the low doses of graphene oxide nanoparticles disturb the functional integrity of the genome, preferentially through endoplasmic reticulum stress signaling, and exhibit a more pronounced genotoxic effect in the normal astrocytes than glioblastoma cells. It's required for careful assessment of potential exposure-related risk for human health, and the data suggests that more caution is needed in biological and medical application of graphene oxide. Thank you for your attention.
Thank you for interesting report. We have some questions. Audience. Thank you, Julia, again.
Thank you
Looking
for the
forward.
opportunity for presenting this result on this conference.
Our next speaker is a student, Darina Mruga, from Institute of Molecular Biology and Genetics of the National Academy of Sciences of Ukraine.
Greetings to everyone. My name is Darina, as it was said, and I would like to present you my work about creation of novel hierarchical magnetical bits on a biodegradable outer layer for targeted delivery. Just a moment. Does the slide change?
Yes, it's okay.
Nice. So the general idea was to create this hierarchical structure with internal magnetic microspheres that would move under the gradient of magnetical field, and the biodegradable outer shell, the outer microparticle, that would degrade and release the drugs that were loaded inside this polymer. And as you can see on the video on the right, these internal magnetical parts were moved using the magnetical pencil, and they respond quite well. So we hoped that this hierarchical structure will move as well. To create this structure, we used two different polymers. For biodegradable one was used gelatin hydrogel, and for biostable magnetic was used polyethylene glycol diacrylate polymer. And on as the magnetic part of this system, we used DINA bits with ferrum oxide. And video on the bottom shows these structures hierarchical, and they move. So it was a little bit of spoiler that we succeed. The creation of the internal beads was made using the microfluidic system with T-junction. The internal diameter of the tubes was 500 microns. And there is the video as they were created. So we have continuous phase of oil and of polymer that were not mixed. And that is why we can see these dots in the tubes, because there is two phases that were not mixing, so we are just making them small dots. The creation requires a high speed of the phases. That is why to polymerize these liquid dots into spheres, we need to firstly create these particles and storage them in a big loop, and then moving these particles from loop through the UV lamp to proceed with polymerization. And as you can see, the polymerization rate was much slower than the creation rate. So after the polymerization, we storage the created magnetic microspheres in the tube, remove the water, not the water, but the oil, and then mix these internal magnetic spheres with the gelatin monomers. And also used the microfluidic system, but the tubes has bigger internal diameter of 1 millimeter. And we also use the same oil phase, and the system was mostly the same. Also, we use the UV polymerization process. And this hierarchical structure has 1 millimeter in diameter, and one sphere contains from 1 to 5 different internal microsphere magnetics. So we tried different polymerization time on internal microspheres to find the optimal one. And we find out that different concentration of ferromoxide particles influence the optimal time of polymerization, and we find out that it was optimal to use about 2.44 seconds for each microsphere in under ultraviolet light to ensure good polymerization. We also tried bigger magnetic particles. The previous one was 1 micron and this was 5 microns, but we found that bigger particles are more sedative, and that is why the homogeneity of this particle was not satisfied. And the speed of polymerization does not affect the duration of the polymerization does not affect the speed of the particles, so it doesn't matter. We also try to create internal particles with different concentration of these ferromoxide particles, and we find out that the maximum concentration that we can produce was 2%, because higher concentration absorb too much ultraviolet. That is why the process of polymerization doesn't go. And it was pretty expected, but the concentration of the magnetic particles inside the internal particles affect the maximum speed of the internal sphere, so it was almost linear. And also we find out that the minimal required concentration for movement under applied magnetic field was 0.1%. So lower concentration wouldn't allow to move our particle in the space. We also found that we can achieve the speed of 12 millimeters per second. It was the mean maximum speed. So after this, we moved on to the creation of this hierarchical structure and checked the optimal polymerization rate for the outer shell, for the gelatin polymer, and find out that, and the ultraviolet degradable ink showed that the best polymerization was with longer duration. So we need at least 2.5 seconds per each sphere to polymerize it whole. Different speed rates of oil phase and polymer phase influence the amount of internal microspheres in the hierarchical structure, but it was quite difficult to find optimal speed rate because this gelatin polymer is temperature dependable, and it is really dense, so it was hard to move it through the microfluidic tubes. But we tried to create these spheres, and we succeeded it. So as you can see, previous one was just prototype with non-polymeric internal spheres, and this one has magnetic spheres. But really high polymerization creation rate deforms this internal sphere, so it will need further optimization. But even these structures were able to move under the applied magnetic field, and the speed of this hierarchical structure depends on the amount of internal spheres, internal microspheres, and it was also pretty linear with some coefficient, but still. So the dependence of the speed of the hierarchical structure on the amount of internal spheres is on the right plot, and the speed of the hierarchical speed of the hierarchical structure with internal spheres with different concentration of magnetic particles is showed on the left. And you also can see that the higher concentration and the bigger amount of internal spheres, the higher the speed. And the maximum speed that we were able to achieve was about 3.5 millimeters per second. So it's about 1/3 of the rate of the internal spheres. So next we check the thermostability of this biodegradable layer and find out that the longer polymerization, the more stable they become under the body temperature. It's 37 degrees. But if we use fast polymerization, we can achieve dissolving in the aqueous solution in 42 hours, which is pretty nice. And after dissolving of this outer shell, the internal spheres are released, and that is why we can remove them from the media. And also at 5 degrees, these spheres were pretty stable for about 150 hours and more. So in this work, we create the procedures for forming internal and external magnetic and external biodegradable microspheres, find optimal polymer compositions for both of these materials, find optimal rates for creation, maybe not for the external microsphere, but for the internal sphere, the optimal rate was found. We check different concentrations that we were able to put inside these spheres, and different time of polymerization, and how these parameters influence the speed. We create these hierarchical microspheres that were able to move under the under the gradient of magnetic field. We check the thermodegradation, and it shows that this hierarchical microsphere have potential for apply in for example, target delivery, but it will need further miniaturization for environmental purification, for example, if this outer shell is loaded with some sort of, I don't know, detergent, I don't know, really, I don't know. But it can also be used as the micro manipulator. For example, the some amount of these beads can surround some particles that should be moved to the another part or something like this. So this is the end of my presentation. Thank you for attention. And if you have questions, I will be glad to answer them.
Thank you, Dorina. And now time questions. Yeah. Wow.
Well, if there is
would
no
like-
question, yeah.
Yeah, I have one question. Also, I would like to use solutions and first question. Have you investigated the ratio between a polymer shell and magnetic core? As your synthesized is a multi-core magnetic system delivery. What was your expectation for the radio between core and shell?
I have not really good connection, but if I understand, you asked about the concentration of biodegradable polymer in the outer shell. Is it correct?
Not exactly. I would like to understand the ratio between the polymer shell and the magnetic peroxide core.
Okay, well, just a moment. So if we're talking about the internal shell polymer mixture, so we used about 10% of polyethylene glycol, 10% of the, just a moment, I will move my, 10% of the photoinitiator. It's lithium phenyl 3-methylbenzophosphonate, and about 80% of water with this magnetic ferromoxide particles. If we're talking about the biodegradable shell, we use 10% of gelatin monomers, 1% of the same photoinitiator, and the rest was just water dissolvent. If we're talking about the ratio of volume of internal particles with the whole hierarchical structure size, you can see this on these pictures. It was not quantified, but I may calculate that it was about, if we have one particle, it was about 10%, something like this.
Thanks.
Yeah. And if we're talking about the force of the magnetic field, it was from 0 to 500 millitesla. So I heard something about the magnetic field. Yeah.
Thank you very much for interesting topic. I have a short question about what method was used for preparation magnetic particles.
Could you repeat, please?
What method was used for preparation magnetic particles?
Okay, yeah, I got it. So these magnetic particles with ferromoxide were bought from Sigma Aldrich, if I'm not mistaken, and it's just commercially available. So.
Thank you, Darina. Thank you for the audience. Interesting board, and we look forward to our next speaker. Each student via Horace. from the Palladian Institute of Biochemistry of the National Academy of Sciences in Nanotechnologies. Thank you. Good morning, everyone. I'm pleased to share our research on mitochondrial specific historians 17 and 72 at the contractile activity of fluid mass. Mitochondria are essential double membrane organelles that produce most of the cell's energy as ATP and store and release calcium ions, which relate to vital processes such as muscle contraction and relaxation. Additionally, mitochondria control cell survival through apoptosis and support overall cellular function. Calcium exchange between the cytosol and mitochondrial matrix is regulated mainly by the calcium reporter for entry and several antiporters for exit. Toxins, energy deficits, pH changes, and other conditions can impair these systems, causing calcium overload to the matrix. This overload interrupts mitochondrial function, triggers oxidative stress, and reduces membrane potential, leading to impaired ATP production. Ultimately, it can cause the occupant of the mitochondrial heterogeneous transition mode, resulting in mitochondrial damage, activation, and cell death. Mitochondrial dysfunction contributes to impaired contractile function of fluid masses in a wide range of pathological conditions. In the myometrium, the smooth features such as interruptions lead to various pathologies, as presented in the slide. Therefore, can be defined as a genus non-toxic compounds that modulate mitochondrial calcium transport and calcium-dependent processes, influencing myometrial fertility remains a significant medical challenge. Oxygens are cup-shaped, nano-sized microcyclic molecules composed of 4 phenolic units linked by methylene bridges. Their unique three-dimensional structure with upper and lower rims, as can be functionalized by various chemical groups, allows selective binding of different ions and molecules. Due to their ability to form stable complexes, oxygens are widely studied by medical research for drug delivery, sensing, and regulation of biological processes. Over the past 3 decades, oxygens have been actively investigated as regulators in muscle projectile activity, affecting calcium transport systems of the plasma membrane, the inner mitochondrial membrane. However, calcium transport systems of the plasma membrane, plasma reticulum, were found to be insensitive to the action of oxygens C715 and C772, which led us to emphasize their specific effect of those compounds on mitochondrial calcium transport systems. This study aimed to determine the influence of oxygens on calcium transport and calcium-dependent processes in isolated nutrients of muscle mitochondria, as well as to assess their effect on the motility of myometrial sleeves. Myometrial mitochondria were previously characterized as having a round to oval shape, size around 500 nanometers, and perinuclear, as well as perimembrane localization. Oxidation of adenine nucleotides in the electron transport chain and the efficiency of mitochondrial inner membrane calcium transport systems are 2 fundamental indicators of mitochondrial functional activity. Both oxygens depended on their concentration, suppress NADH oxidation and isolate mitochondria, which we attribute to the effect of complex 1 in the electron transport chain.
This effect results in a decrease in electrochemical potential and is associated with reduced calcium accumulation in the matrix. We found that study compounds effectively reduce energy-dependent accumulation. Nitric oxide plays an essential role in the contractile function of this mass. Mitochondria can produce NO via calcium-sensitive mitochondrial inositase. Therefore, a decrease in a calcium accumulation is expected to directly affect this production process. Indeed, we demonstrated that oxorines significantly inhibit NO synthesis in isolated mitochondria. Furthermore, flow cytometry confirmed this effect in intact myocytes. Radiolipin, a unique phospholipid of the inner mitochondrial membrane, induces membrane curvature amongst dense vacuum of protein complexes. Plays a key role in the structural stabilization of the electron transport chain, supports optimal calcium handling, and modulates mitochondrial nitric oxide synthase activity. The new ecridine orange bromide is a cardiolipin-specific dye. When mitochondria are added to a medium containing NaO, the fluorescence increases due to its interaction with cardiolipin. The subsequent addition of oxorines to the same medium led to substantial reduction in NaO fluorescence. We attribute this effect to the interaction of oxorine with the inner mitochondrial membrane, which is highly enriched in cardiolipin. Using commercially available cardiolipin, predominantly in the petrolipid available form, and applying direct infusion electrospray negative ion, what we call tiny flight mass spectrometry, we repeatedly detected doubly charged, doubly deprotonated molecular ion corresponding to the complex of tetralinear oil, cardiolipin with oxorine C715. Taken together, the chemical findings suggest that oxorines may influence the chemical activity of the mind. Using tensometry, we found that C715 at 30 micromoles significantly increased both the amplitude and frequency of spontaneous contractions in red bilateral strips by approximately 20-25%. Full mechanokinetic analysis showed that the compound enhanced several force line impulse parameters, individual compression, and relaxation cycles, while reducing the loss of contraction and relaxation velocities. These effects are consistent with the compound's ability to suppress mitochondrial calcium accumulation and nitric oxide synthesis, both isolated mitochondria and intact myocytes. In suspension, myocytes have a round to oval shape, which makes it possible to use the laser population spectroscopy to measure characteristic size. Similar to the uterine agent oxytocin, C715 reduced the hydrodynamic diameter of isolated myocytes in agreement with the tensometry results. Notably, the effects of C715 were comparable in magnitude of those and oxytocin at similar sequential. Although the effects of oxorines in mitochondrial function were primarily studied in isolated mitochondria, verifying whether these compounds can enter intact myocytes remains essential for interpreting their potential activity under physiological conditions. Address this. One of the objectives of our work was to visualize the entry and intracellular localization of a fluorescent labeled oxorine analog using fluorescence-based methods. Fluorescent isothiocyanate functionalization of macromolecules in biologically active compounds is a common practice for studying their localization and properties. We functionalized the oxorine ball with two FITC molecules. Results obtained by laser microscopy demonstrate clear localization of the mitochondrial specific fluorescent probe tracker with the oxorine FITC conjugate. This is a considerable argument for the possibility of penetration of microcycle ions into the cell and the precondition for the interaction with cellular structures. If you don't mind, I skip all the conclusions. We are deeply grateful to our colleagues in the assistance and valuable guidance. Thank you for your attention.
Thank you for your presentation and the integration. No question in Zoom. Thank you again for the interesting presentation. And the next speaker, PhD student Valery Kovac from Uzhhorod National University.
Hello, do you hear me?
Yes.
Sorry, I have some issues with my webcam. So if it's possible, can I turn on the presentation only?
You can start your presentation.
Thank you. One second, please. Okay. Do you see my screen?
We see your presentation, but not in full screen mode.
Not in full screen?
Yes. First, you must run your presentation in full screen and then share you in Zoom.
Okay, sorry. Okay. And now,
Yes, it's okay. You can start your presentation.
Thank you. So I would like to present our work with our colleagues. Electroluminescent of the CMIN moleculars immobilized on the graphene surface. In this experiment, we were investigating the changes in the structure of nucleic acid, which is induced by so-called low-energy secondary electrons, which are generated in large quantities when a stream of high-energy radiation pass through biological media. As a result of collision of these electrons with the components of such macromoleculars, in particular with nitrogen bases, excitation of the electronic vibration states of these moleculars occurs, followed by radiative deci through various channels with different probabilities. Therefore, the luminescence properties of nucleic acid based significantly complement the physical picture of the process of their inlets interaction with electron and photons. A characteristic feature of the luminescence of nitrogens based under normal condition in this low quantity yield, which is due to the complex structure of these moleculars and the manifestation of various quantities processes. These examples, the limited number of studies on the mechanicals of electron indicated luminescence. The aim of the process in this report is investigation the luminescence of the nitrogen-based CMIN under the action of electron bombarded under conditions where these moleculars are immobilized on the surface of the graphene matrix. Previously, we studied this issue by using the nitrogen-based cytonin. So a few words about methodology and experiment which we are presenting here. The experiment were carried out using the universal ultra vacuum system. This system can give us opportunity to decrease pressure lower than 10 in minus 7 Pascal, which operate in the mode of electron photon spectrometer. So we were using an energy of 600 electron volts and carrying density of 1.4 milliamperes per centimeter square. Photon emission in the value of range in from 200 to 600 nanometers. We're analyzing using our monochromator, which optical axis formed an angle of 45 degrees with surface and normal of this surface. The angle of incident of the electrons were varying from 60 degrees to 70 degrees. The emission was detected using the photomultiplier. The measurement of the electroluminescence spectrum were carried out in ultralight vacuum conditions above 5 in minus 7 Pascal. An electron beam with energy of from 500 to 800 electron volts were using, the current density of which was about 0.05, 0.3 milliamperes per millimeter square. Our semin molecular is showing here. The molecular was formed, its structure is shown on the figure. The temperature point was 316, 317 Celsius degrees. And the immobilization of biomolecular was carried out by preparing from the temperature of 110 Celsius and in minus 1 Pascal in the working chamber. The matrix dimensions are 10.10.2 millimeters. The surface was mechanically cleaned before the depositing of the biomolecular inside. In the figure 3, we can see the luminescence spectrum of a graphene surface with absorption, nitrogen-based semin molecular. It's the spectrum number 1 under the action of an electronic beam with an energy of 600 electron volts and a current density of 0.1 milliamperes per millimeter square. The luminescence of the pure graphene surface is represented by spectrum 2. The difference between spectrum 1 and spectrum 2 correspond to the luminescence spectrum of semin molecular embedded in the graphene matrix. Luminescence spectrum 3 consists of 3 broad bands. The maximum of the first located at a wavelength of 313 nanometers. The second was on 413 nanometers, and the third was at 490 nanometers. It is assumed that the mechanism responsible for these bands are different. In particular, for the first band, under the action of the electron beam excited of the p electrons of the semi molecular occurs from the ground single state S0 to excite single state Sn. Subsequently, distinction of the Sn state to the first system S1 takes place at its radiative density gives there to the first band. This band will be considered the fluorescent band of our measurement. The second band corresponds to photophorest photosphor sorry, which according to physical concept appears at long wavelengths. Photophosphorus luminescence, sorry. It occurs required electronic impact exciting of the p electrons of the semi molecular from the ground single state S0 to expand stripe states Tn, followed by deactivation to state T1 and radiative necessity to ground states S0. Another change for population, the T1 state is the intersystem crossing from S1 to T1 from state S1. Notably, such interstate crossing in the case of optical exchanges of moleculars often become the main reason for the appearance of phosphorescence. As for the third band of 100 nanometers, its physical origin remains unclear. It should be noted that under election of energy is transformed to the matrix and to the semi-molecular ambient in it. Therefore, energy is possible from example from exchange of the matrix to semi-molecular, which can influence the luminescence of
It looked like Valerie has issues. Isn't it not connections? Valerie? Yes.
Do you hear me?
Yes, Valerie.
Sorry,
Please
I had some
launch your
internet
presentation.
problems. So my connection shut down. I'm back. So can I go to the conclusion if it's possible? I'm
Yes,
sorry
please.
for the situation. So if, a few words about conclusion in our presentation. The study of the luminescence phenomena of the nucleic
Oh, I'm
acids.
sorry. Now we can see your slide.
Yes, sure. 1 second. Yes. Yes. I'm coming back. Sorry. And now, okay.
Yes, okay.
Yes, conclusions. Sorry. So our study was based on the semin moleculars which are embedded in a graphene surface under the action of 600 electron volts in ultra vacuum condition, lower than 5 in 10 minus 7 minus 8 Pascal. In the luminescence spectrum of semin moleculars embedded in the graphene substructure obtained using 600 electron volts in our ultra vacuum system, we occurred few primary points of our curve to change in 335 nanometers, in 435 nanometers, and in 495 nanometers, which you can see on the curve number 3. So we understand the behaving of first two bands in our curve, and we were discussing them in our work. So about the curve number 3, the molecular band with a maximum and 435 nanometers are corresponding to photophosphorics and is caused by the radiative transmission from T1 to S0. It has been shown that fragmentation of semin moleculars immobilized in the solid matrix under electronic bombarding using energy of 600 and 800 electron volts is negligibly small, and effect is pretty small. Therefore, adsorption of biomoleculars on the surface of a solid body can protect them from degradation in the surrounding environment. So thank you. That will be all.
Thank you, Valerie. Now we have find the questions. No questions, so thank you again. Now we have a small of the break. All participants inside can enjoy this
Thank
coffee
you.
or tea with sweets. And we will continue at 45. So we have about 10 minutes. So see you soon.
Thank you very much.
Excuse me, may I try to share my screen, my presentation right now, just to probe to share my screen? If there is anybody, so it means yes. Excuse me, may I probe my presentation? Can you hear somebody me?
Hello, no, we have coffee break now,
Hello.
and we have now coffee break, and your presentation at 12:30. Your time.
Sorry, I just
after
wanted
2 hours.
I just wanted to check if everything is correct because I have two monitors. I'm not sure that how it will be. Can I try or it's a problem?
You have checked if you
Yeah,
You have
I prefer to check if you don't mind.
yes, you may check.
Okay, just I will share screen. Okay, too many. Okay, can you see it? And if I do,
Yes, we see, but not full screen.
so it's better to.
No, at first you must run presentation on
And
full screen.
now,
And
can you see full screen, right?
yes, it's okay.
Okay. Thank you very much. Sorry for disturbing.
Yes, and
Dear colleagues, we continue our morning session. And I invite Professor Elena Rogacheва from National Technical University, Department of the Technical Institute.
Yes, I'm here. Just a moment. Good morning,
Dear Professor
dear colleague.
Rogacheva, if you're ready, please take your floor.
Good morning, dear colleagues. The topic of my presentation, you can see temperature dependencies of kinetic properties of semiconducting polycrystalline bismuth antimony films. The work was performed in National Technical University, Kharkiv Polytechnic Institute. A few words about background and motivation of our work. Bismuth antimony solid solutions are very interesting objects from point of view of scientific, of solid-state physics, nanoscale physics, and practical applications in spintronics, thermoelectricity, etc. Bismuth antimony are continuous series of solid solutions. You can see a phase diagram and crystal structure, the same in all compositions, in which in this system band structure changes in a complex manner. Near x is equals 0.6, the transition from semi-metal to semiconductor occurs, and at x equals 0.09, transition from indirect semiconductor to direct semiconductor takes place, and the highest values of thermoelectric figure of merit take place. It should be noted that thermoelectric materials are usually solid solutions, and one of the methods of improving their properties, thermoelectric efficiency, is the method of solid solution. As thin films are increasingly being applied, it is important to know what occurs in solid solutions in the thin film states. Solid solution based on bismuth antimony are well known as the best materials for the thermoelectric cooling. Currently, thermoelectric energy converters are widely used in science and technology, and their areas of application are expanded. The thermoelectric converters based on bismuth antimony in the thin film states are being used more and more widely. Recently, it has been discovered that bismuth antimony is 3D topological insulator, and the studying transfer properties has grown sharply. Bismuth stibium at x 0.1 was the first topological insulator. Topological insulators are stretch materials, insulators on the inside and conductors on the surface. They have properties that make them excellent development of spintronics and thermoelectricity. Yeah, I repeat that bismuth stibium was the first topological 3D insulator. Motivation of this work, Earlier, we first observed at room temperature in the bismuth antimony crystals and films, concentration dependencies anomalies of transport properties, and attributed them to a percolation, gapless state, and semi-metal semiconductor transitions. Besides, we observed classical and quantum size effects in bismuth antimony thin films. Will these features be observed at other temperature in thin films? This question. To answer this question, it was necessary to obtain the temperature dependencies of the kinetic coefficients for different composition, for different thicknesses. It is required a wide range of work related to establishing the influence of composition, temperature, thin film thickness on the transfer properties of the films. Here we first observed, I said, concentration anomalies and classical and quantum size effects in this system. We first. That is why the object of the present study, semiconductor polycrystalline bismuth antimony thin films with X is 0.09 and thicknesses 50 from 50 to 300 nanometers. The goal of the work to measure temperature dependencies of kinetic properties in the range 77-300 Kelvin. What is these properties? Electrical conductivity, Hall coefficient, charge carrier mobility, magnetic resistance, and thermoelectric characteristic, power factor, and figure of merit. Experimental detail. I will skip the experimental details because we don't have time. I just want to mention that Hall coefficient and electrical conductivity were measured in the temperature 77-300 Kelvin using a conventional DC method. The measurements were carried out on thin films with 6 contacts. The error in the Hall coefficient and electrical conductivity measurement did not exceed 5%. Based on the obtained values of Hall coefficient and sigma, the charge carrier concentration and charge carrier mobility were calculated as this formula you see. The type of conductivity were determined by sign Hall coefficient. They have electronic conductivity. For correct interpretation of results of galvanomagnetic measurements, particularly when studying temperature dependencies of kinetic properties, it is necessary to use weak magnetic field in which Hall coefficient remain constant. The boundaries of weak and strong magnetic fields were determined using dependencies of Hall coefficient and magnetic resistance on magnetic field. For it was established that for films, the boundary of a weak magnetic field is at least 1 Tesla. This value significantly exceeds that for bulk, which we attributed to substantial reduction of mobility due to defects and defects of surface defects, etc. in thin film state. These are shapes of samples for measuring electrical conductivity and the Hall coefficient of thin film and bulk crystal. We investigated a bulk crystal and thin films. Now, results. Temperature dependencies of kinetic properties of our films. In this figure, you can see the temperature dependencies of Hall coefficient, electrical conductivity, mobility, electron concentration, first for bulk crystal. from which we obtained the films. And below, you can see temperature dependencies, these characteristics, these properties for thin film, thick thin film with thickness 270 nanometer. If compare these figures, well, it is seen. It can be seen that the nature of dependence, temperature dependence of electrical conductivity is exactly the opposite from bulk crystal and thin films. Next figure, the same dependencies, all these kinetic characteristics, kinetic coefficients for thin film with thickness 160 nanometer. And in this figure, temperature dependencies for film with thickness 58 nanometer, more thin films. No, you can see that general character of these dependencies is the same, but differs by value of these characteristics. In this figure, you can see temperature dependencies, relative electrical conductivity and Hall coefficient for thin films with D 270 and 58 nanometer, for thick film and thin film 170 and 58. We can see that these dependencies, character is the same, but value of this characteristic is different. Thickness influence on this characteristic. In this picture, this same picture, only I add the dependence for bulk crystal. You can see again that this characteristic differs. Discussion. Many characteristics obtained in discussion. First, the nature of temperature dependencies of electrical conductivity for crystals and thin films is qualitatively different. For crystals, the thermal resistance coefficient is positive. For films, negative. Oh, this film you saw. Next, the rate of decrease of electrical conductivity with temperature increases as D thickness decreases. And lower values of electrical conductivity in films compared to crystal can be explained by the increasing scattering processes in thin films due to increase in contribution of scattering services and the presence of defects of various types. The fact that at room temperature, the value of electrical conductivity of thin films and crystals practically coincide can be qualitatively explained by the fact that values of the charge carrier concentration and mobility of at room temperature are close both in crystals and films. The difference I again show this, the difference in temperature dependencies of electrical conductivity of bismuth, antimony thin films and bulk crystal can be explained by analyzing the temperature dependencies of concentration and mobility of charge carriers. For thin films and bulk crystals, concentration increases with increased temperature, and mobility decreases. For bulk, with increased temperature, the N increases more slowly than mobility decreases, and electrical conductivity decreases. In films, due to additional scattering of carriers by surface, boundaries, etc., the dependence of temperature dependence of mobility is not as strong as in bulk crystals. As a result, with sufficiently small d thickness, the growth of concentration with temperature is faster than decreasing mobility, and sigma electrical conductivity increases. As d increases, the relative contribution of scattering by surface and defects decreases, and the dependence, temperature dependence of electrical conductivity of a bulk crystal approaches the bulk crystal. The fact that sigma of films with smaller d increases more slowly than that of films with larger d thickness may be associated with a lower rate of increase in concentration with temperature in thin films. The power factor for mobility in the temperature dependencies concentration is for thick films, 270, and for thin films, different 2 and 0.8. This is obviously related for a higher chaos concentration in films. Magneto-resistance. For all investigated thick films, 270, 300 nanometer, the magneto-resistance decreased with increasing temperature, which is consistent with a decrease in mobility as grown in temperature. Analyzing the obtained results, it can be seen that value of magnetoresistance of the bulk crystal is much higher than that of thin films. That a decrease in thickness leads to a further decrease in magnetoresistance. The rate of decrease in magnetoresistance with temperature decreases under transition from bulk to thin films, and when the film thickness decreases. In the range 77-300, magnetoresistance decreases by 20 times for bulk and by 5 times for films with D 270 nanometer. It is the main parameter. No, it is known that the main parameter that determines the change in magnetoresistance with temperature, mobility. Therefore, the observed regularities can be explained by corresponding behavior of mobility. And the influence of thickness on the behavior of temperature dependencies, electrical conductivity, and concentration dependencies in thin films was established. The obtained dependencies were compared with the corresponding dependencies for bulk crystal. For bulk crystal, it is important, for bulk crystal and annealed thick films, the temperature dependencies charge carrier concentration and electrical conductivity correspond semiconductor conductivity. Exponential. The width of the forbidden for the back for film with D 270 nanometer, delta E 40.2 milli electron volt. But the temperature dependencies of electrical conductivity for sufficiently thin films or unannealed thick films in coaster-to-bulk crystals and annealed thick films can be described by power. And conclusions. All films studied had N-type of conductivity, similar to the bulk crystal. For films, the boundary between weak and strong magnetic field is 1 Tesla and significantly exceeds B for bulk crystal due to reduction in mobility in thin films. The transition to the thin film state leads to an increase in the charge carrier concentration by almost an order of magnitude and to a sharp decrease in magnetic resistance. The temperature dependence of electrical conductivity of bulk and thin films are qualitatively different, which explained by additional scattering of charge carriers by the surface of films. For bulk crystal and thick films, the temperature dependencies of electrical conductivity and concentration charge carriers dependencies correspond semiconductor conductivity, but for thin films and unannealed thick films, the dependencies can be described by power function. The obtained results are important for both for the development of concepts of nanophysics and for practical application. Thank you for your attention.
Thank you for your report. Next questions. And no questions.
Excuse me, I have a question if there is time. Hi, Elena Ivanovna. I just wanted to ask that you show this temperature dependence of conductivity for bulk crystals, but I saw on one it is metallic, in another semiconducting. Why is it happening? Is it typo or what is it?
You are right, but this semiconductor is degenerated semiconductor. And temperature dependence of conductivity, the same in metals.
Yeah, but you have like figure where you have two dependencies for the bulk. If you return to your slide where you show the this bulk conductivity. So the previous here. So you can see at the top you have sigma, which is increases within temperature, decrease, and in another in opposite. What's happening?
You are right. You are right. I did not say about that, but increase in electrical conductivity at the temperature to 150 is a result of semiconductor type of conductivity.
Okay.
I can this question, but this effect is known, and I because much time.
I can read your paper. Thank you very much. Yeah. Sorry for this too. Okay, thank you.
Thank you very much for
Thank you for the
questions.
discussion.
Thank you very much.
And we move forward. Our next speaker is Dr. Irina Konchakova. She represents State University of Trade and Economics in Ukraine and the University of Andrews, France. Dr. Goncharova is here.
Okay. Yes, I'm here. Hello, everyone. And I would be sincerely grateful to the organizer committee for giving me such an opportunity to share my screen, please.
Yes, please. You can share your screen.
Okay, now did you see screen?
Notes.
Okay, now everything is clear.
We see your presentation, but not in full screen mode.
Okay. In this case, probably I will increase my screen.
Sorry, one moment. Could you please launch full screen mode?
Excuse me, did you see my screen right now?
We see your presentation, but not in full screen mode. Please, could you launch full screen?
Okay. And now everything is clear?
You must switch off demonstration, then launch full screen mode presentation, and then
Stop share. And then again. And now. Now everything is okay?
Yes, now it's okay. Please take the floor.
And just in case I need to show, and second slide, is it possible to see second because okay. Probably if I will show you my presentation only without full screen, it will be okay or not? Because
sorry, I'm on and you switch off this. Yeah, now it's okay.
It's okay? Now everything is good? Okay. Did you see my screen? Okay. Okay, thank you very much. Hello everyone, my name is Irina Goncharova. I have PhD degree on chemistry and I'm associate professor at the Department of Commodity Science and Pharmacy, State University of Trade and Economics, Kyiv, Ukraine. At the same time, from May 2022 to July 2024, under the special programs for Ukrainian scientists, Pause Solidarity with Ukraine and Pause NR Ukraine, I worked as a research scientist in Maltech and Photonics LFS Matrix Laboratories, University of Angers, France, under the scientific directions of Professor Bushta Sakhrai. Therefore, the title of my today's presentation is Laser-Induced Breakdown Spectroscopy Application for Metallic Ions Detection in Aqueous Solutions and Natural Waters. Scientific Supervisor, Professor Bushta Sakhrai. Research Team, Dr. Dominique Gouchon and Dr. Philippe Rouquet. On the next slide, you can see research laboratories of the University of Angers, Maltech Anjou, and Photonics LFS Matrix, as well as research team of my scientific supervisor, Professor Bushta Sakhrai. We work together with colleagues from France, Poland, Morocco, Turkey, Kenya, and Ukraine. As part of my scientific project at the University of Angers, in chemical laboratory by myself, I prepare samples of aqueous solutions and natural waters of France. Then in the laser laboratory, together with colleagues of LFS Matrix, we conducted research of the samples using the laser technology. And finally, in the physical chemical laboratory, together with colleagues of Maltech Anjou, we conducted ultraviolet and visible spectroscopic measurements of water samples in comparison with laser experiments. The novelty of the research has no doubt, because, as everybody knows, water is the most important natural resource, substance number one, without which the existence of living beings on Earth is impossible. Clean drinking water is a main key to a healthy life of the population, especially present time. Due to this terrible war in our native country of Ukraine, the problems of water quality, monitoring and purification are the most urgent. Unfortunately, the missile strikes have accompanied not only by consequences for people, animals, and infrastructure, but also the environment suffers from it: air, water, soil. Therefore, water quality monitoring is an important part of environmental management and protection. It's known that most of the current detection techniques for water quality monitoring are based on the traditional optical and mass spectroscopy measurements. However, these methods require a long detection cycles, and some of them need to use of specific chemicals which may cause secondary pollutions. In this case, laser-induced breakdown spectroscopy has lots of advantages, such as easy sample preparation, fast and simple operation, and chemicals-free during the process. So, laser-induced breakdown spectroscopy, which shortly calls LIBS. This is novel, atomic emission, spectroscopic nanotechnology that offers precise quantitative chemical analysis using high power pulsed laser. It's known that this laser was created in 1960 by Mayman in California, USA. However, the first application of LIBS on aqueous samples was only in 1984, 3 years after the introduction of the LIBS acronym by Radziemski and Luria. Most of the research of the LIBS analysis for water and aqueous solutions has been carried out in China, following them USA, Germany, France, Italy, Spain, and Canada. The LIBS technique has practical application in chemistry, ecology, medicine, pharmacology, food industry, and commodity science. It's known that typical LIBS system includes 5 main components. These are the sample holder, the laser source, the spectrometer, and the data analysis unit. For the experimental setup for the first series of experiment, our research team used single pulse LIBS consist high power laser continuum mini-lead with a pulse direction of 10-15 nanosecond, a repetition rate of 10 Hz, a maximum pulse energy of 850 millijoule, and output and the wavelength of 1064 nanometer with USB 4000 ocean optic spectrometer. It's known that direct analysis in water by LIBS following the problems of droplet splashing and laser energy decay. Therefore, in this study, our research team focused on the application of chemical replacement combined with surface-enhanced LIBS for the detection of alkaline metallic ions such as sodium, potassium, as well as mixture in aqueous solutions and natural waters of France. First of all, the aqueous solution, the main aqueous solution with concentration 500 microgram per milliliter for sodium and potassium chloride were dropped into aluminum alloy plate and dried on aluminum foil. Therefore, LIBS experiments for aluminum alloy plates also were conducted. LIBS spectra containing information about all of these elements were collected in visible and near ultraviolet optical spectrum region immediately after microplasma generation. On the next slide, you can see the composition of aluminum alloy plate as well as LIBS spectra of these plates. Besides the main element aluminum, it contains of the small amount of such elements as silica, iron, copper, manganese, magnesium, chromium, and zinc. From the next slide, I would like to show you experimental procedure. First of all, I would like to show you about main solution, sodium chloride. From the crystal sodium chloride in chemical laboratory, I prepare solution 500 microgram per milliliter sodium chloride. And then after conducting LIBS experiment and receiving LIBS spectra, we compared it with theoretical database LIBS NIST of American National Institute of Standard and Technology. You can see, and we found, compared to with the LIBS NIST, we found all of 3 peaks which corresponds with sodium with biggest wavelength 589 nanometer. Then on the next step, from the main solution 500 microgram per milliliter on the biggest wavelength, by dilution with distilled water, we prepare 7 standard solutions with range concentrations from 30 to 210 microgram per milliliter for sodium chloride. And after conducting the LIBS experiment for the same methodology, receiving LIBS spectra and building the calibration cover, we calculated limit of detection for sodium, which equals 0.162 microgram per milliliter. On the next slide, I would like to show you the same experimental procedure for the potassium chloride with concentrations 500 microgram per milliliter. in chemical laboratory, we prepare this solution from the crystal potassium chloride. And after conducting LIPS experiment in macroplasma generation, we compared two peaks regarding to the American database LIPS NIST. From the main solution, 500 microgram per milliliter, by analogy with sodium chloride, we prepare 7 standard solution with concentration from 30 to 210 microgram per milliliter. Then build the calibration curve and calculate the limit of detection, which equals for potassium 0.193 microgram per milliliter. After conduct LIPS experiment with unitary solution, sodium and potassium chloride, on the next step, our research team performed the LIPS experiment with mixed solution, sodium and potassium chloride at the same time. So on the next slide, you can see, first of all, first figure corresponds to the LIPS spectrum, unitary solution, 250 microgram per milliliter, sodium chloride. You can see 4 peaks. First of all, correspond to the aluminum alloy plate, and 3 peaks correspond to the sodium with biggest wavelength. On the next slide, on the next figure, you can see LIPS spectra of unitary solution, 250 microgram per milliliter. For potassium chloride, we found here 3 peaks. First of all, correspond to the pure aluminum alloy plate, and 2 peaks correspond to the potassium with the biggest wavelength, 766 nanometer. And finally, third figure corresponds to the mixed solution, the same concentration, 250 microgram per milliliter for sodium and potassium chloride, and at the same time percentage 50-50. And we found here all of 6 peaks. First of all, first peaks for a pure aluminum alloy plate, 3 peaks for sodium, and 2 peaks for potassium. Okay. After conducting LIPS experiment with aqueous solutions as theoretical foundation, on the next step, our research team performed LIPS experiment with natural waters of France. First of all, we conducted experiment with tap water from chemical laboratory Elfia, and then natural water from lake, rivers, and even seawater from Atlantic Ocean. First of all, I would like to pay your attention for tap water, chemical laboratory Elfia. Here we found, we conducted LIPS experiment for the same methodology, and after microplasma generation, we found we found peaks for sodium, and using the calibration curve for aqueous solution sodium chloride, we calculated real content of sodium. We found also, research team found very good agreement with maximum permissible concentration World Health Organization for drinking water. In our case, it was 10 microgram per milliliter, maximum permissible concentration 20 microgram per milliliter. Second sample, it was the main lake Angers. We found content of sodium, which equals 45 microgram per milliliter, and comparing to the maximum permissible concentration, 250 World Health Organization, therefore we found very good agreements. Then next sample, third and fourth samples in St. Nicholas Lake and Jardin du Plan Lakes, Angers. We found, in first case, we found content of sodium, 58 microgram per milliliter, maximum permissible concentration is 250, and Jardin du Plan, in case of Jardin du Plan Lake Angers, we found sodium and potassium at the same time, sodium 87 microgram per milliliter, maximum permissible concentration 250, and in case of potassium, it was 1.2 microgram per milliliter, and maximum permissible concentration 100 microgram per milliliter, regarding to the World Health Organization, natural waters. As an example, it was main river Angers. Our research team found here sodium and potassium at the same time. Content of sodium was 150 microgram per milliliter, maximum permissible concentration 250, and potassium only 21 microgram per milliliter with maximum permissible concentration 100, regarding to the World Health Organization for natural waters. An example, it was from Loire River, Nantes. We found here also sodium and potassium at the same time. Sodium 182 microgram per milliliter with maximum permissible concentration 250, and potassium 57 with maximum permissible 100. And on the next slide, I would like to show you samples for Seine River Paris. And in this case, I would like to pay your attention that in case of sodium, we found an increase, amount of sodium was increased. We found 300 micron per milliliter, but at the same time, maximum permissible concentration was only 250. With potassium was everything good, 75 and 100, regarding to the maximum permissible concentration. In this case, situation with sodium, I can explain that Seine is the main river of France, and of course with lots of visitors. It's my explanation. And after conducting LIPS experiment with samples from lakes and rivers, on the next step, we conducted LIPS experiment with seawater from Atlantic Ocean, Lissamble, Dallon. But of course, taking into account that seawater contains the biggest amount of sodium chloride, before conducting LIPS experiment, we made dissolution with distilled water in 50 times, and after that conducted LIPS experiment for the same methodology, and after that we found good agreement with maximum permissible concentration of World Health Organization for sodium 0.6 gram per liter, maximum permissible concentration for sodium range 30-35, and potassium concentration for potassium, it was 55 microgram per liter, and maximum permissible from 50 to 100 microgram per liter for seawater, regarding to the World Health Organization. Also, in the next step, I would like to show you my main publication concerning LIPS, laser induced breakdown spectroscopy. And first of all, this review article in Spectrochemical Octopod B atomic spectroscopy. The title, Laser Induced Breakdown Spectroscopy Application for Heavy Metal Detection in Water, a Review. Scopus Web of Science, Impact Factors, the first and corresponding author. And this article was published 1 year ago in July 2024. And for the present time, this article has already 15 citations in Scopus, 17 ResearchGate, and 23 citations in Google Scholar, and lots of recommendations. And second, my main publication, Spring on Nature chapter, Laser Induced Breakdown Spectroscopy as a Promising Nanotechnology for Cadmium and Chromium Detection in Aqueous Solution. Scopus. I was also the first and corresponding author. So next slide, I would like to show you my main list of publications concerning LIPS, and finally conclusions and future perspectives. Therefore, laser induced breakdown spectroscopy. This is advanced nanotechnology for monitoring and protecting the water resources which are essential for public health, agriculture, and economic development. Experimental results show that LIPS is prospective method for improving the detection sensitivity of alkaline ions, sodium, potassium in aqueous solutions. At the same time, LIPS technique used for the quality monitoring of natural waters of France on sodium and potassium ions. On the next step, our research team would like to conduct a scientific experiment on the detection of metallic ions in natural waters of Ukraine. And this is very important for well-being and general around the world, and practically for Ukraine in this difficult period of war. This work was supported by special French programs for Ukrainian scientists, PAU Solidarity with Ukraine, PAU CNR Ukraine, as well as French Embassy in Ukraine Campus France, and researchers from the scientific team of Professor Bushta Sakhrai, University of Angers, France. Thank you very much, and do you have any questions?
Thank you, Dr. Goncharova. And we have time for one small question.
Here, one question from one friend. So,
Thank you. And could you please compare the speed and cost of water analysis with your method and alternatives like chemical methods?
Yes, but yes, I understood your question. Thank you so much. I will show, because I show the slide at the beginning. Now I will try to repeat the slide. Because compared to the currently available water, compared to the currently available water quality monitoring method and techniques, LIPS has several advantages, because In my report, in my presentation, I told that it's known that most of the current detection techniques, for example, atomic absorption spectroscopy, atomic fluorescence spectrometry, HPLS, high performance liquid chromatography, JELSA, has a low detection cycle, and some of them need to use of specific chemicals which may cause secondary pollution. But in this case, our method, laser-induced breakdown spectroscopy with shortly whole slips, has lots of advantages. For example, easy sample preparation, very easy, fast and simple operation, and chemicals free during the process is very important. Its main advantages of laser-induced breakdown spectroscopy comparing to the currently available water quality monitoring method and techniques.
Thank you. And, we move forward. Our next speaker, Professor Eugen Land from the Human Institute for Metal Physics of the National Academy of Sciences of Ukraine. Professor
Okay,
Land.
thank you very much. Thank you very much. And I would be sincerely grateful to the organizing committee for giving me such an important opportunity to make my oral presentation. Thank you very much.
Again, schedule. And we wait for Professor Eugen Land.
Can I
Professor
share?
Eugen Land. No. Yes, please share your presentation. Please launch it in full screen mode.
Do you see my presentation?
Yes, we see, but not at full screen mode. Maybe firstly try to launch in full screen mode and then share your screen. Share your window with presentation.
I bet hear you. Do you see the full screen?
Oh, please stop sharing screen, launch in full screen mode presentation, and then share your window with full screen mode presentation.
Sorry. Good afternoon. I'm pleased to present our work devoted to new quantum materials based on functionalized graphene nanostructures. Monolayer, bilayer, and multilayer graphene, as well as various...
Sorry to interrupt you, but your slides need more. You now launch full screen mode, yes?
I don't hear you.
Do you launch full screen mode now? Oh, now we see you presentation in constructor mode, not full screen mode.
Може, спробуйте українською, бо англійською щось я не розумію, що ви кажете.
Ми бачимо вашу презентацію у режимі конструктора презентації, але не в режимі повного слайду.
У мене вона розшарена в повному екрані.
Зрозуміло. Тоді ви маєте підтримати трансляцію екрану і запустити знову, вибрати повний режим. Вікно із режиму світу.
Да, добре, зараз. No, it's okay.
Oh, but we continue that slide. This
Я вибачаюсь, у вас голос дребезжить, і я не можу розібрати, що ви кажете.
в повному режимі, але залишаємо як є. Дитина щось робити зараз переговорити слайди, щоб ми бачили, що дитина змінюється.
Навіть українською я не розберу, що ви кажете. Ви бачите повний екран чи ні?
Ні, ми повний екран не бачимо,
Ага.
але хай залишається вже як є. Пробуйте переключити слайди, щоб вони переключалися.
Так переключаються? Чи не
Ні,
переключаються? Ні?
не переключаються. Ні. Можливо, давайте ви нам вислите презентацію на пошту, і ми будемо її демонструвати. Так швидше буде. А зараз ми до іншого доповідача, а потім до вас вернемося.
Добре.
So, some change, and our next speaker will be Dr. Valentin Provera from Verkin Institute for Low Temperature Physics and Engineering of the National Academy of Sciences of Ukraine. Dr. Provera, we see you.
Can you see my screen?
Yes, that's okay. So please take your floor.
Good afternoon, dear participants. The title of my report is Superconducting Nanobridge during electrical breakdown of a dielectric nanolayer. Superconducting magnets and quantum interferometers are the basis of applied superconductivity. The main element of a modern circuit is the Jefferson film junction. Typically, Jefferson film junction is manufactured using complex and expensive high vacuum equipment. We have proposed and investigated a new effective method for manufacturing Jefferson film junctions in the form of a superconducting nanobridge without the use of expensive equipment. Such a bridge is formed in fractions of a microsecond during controlled electrical breakdown in air of a dielectric nanolayer between two film electrodes. The nanobridge that appears as a result of breakdown has a length and diameter close to the thickness of the dielectric and consists of a cathode film material. The obtained critical current value at a temperature of 4.2 Kelvin is close to the known theoretical value for short Jefferson bridge. A superconducting bridge was created for the first time by electrical breakdown of a dielectric layer between two superconducting films of niobium and lead about 50 years ago. It was shown that such a bridge has Jefferson properties and that a superconducting quantum interferometer can be created on its basis. At the same time, a number of its properties have not been studied. This include the dependence of the normal resistance of the bridge on the breakdown current, the dependence of the breakdown voltage on the shape and material of the electrodes, the value of the diameter of the bridge, the effect of the dielectric material on the resistance of the bridge. Firstly, we used a method of smooth increase in voltage. For this purpose, we investigate this structure. Fig 1 presents a schematic representation of the cross-section of the experimental sample of the structure consisting of the upper electrode in the form of the film disc with a diameter D from an indium tin alloy. This is cathode, a layer of niobium oxide, and the lower electrode in the form of niobium film on a silicon substrate. Fig 2 presents photo of this sample with 10 indium tin film disc with a diameter of 0.9 millimeter. Niobium oxide with a thickness of 30 nanometer is formed by electrochemical method. An alloy film with a thickness of 100 nanometer is deposited by thermal evaporation. Fig 3 presents dependence of the dielectric voltage on generated voltage. As you can see, electrical breakdown observed at 12-13 volts for thickness of dielectric 30 nanometer. Fig 4 presents the spread of resistance values R sub 1 of 3 series of bridges with 10 bridges in each series obtained as a result of breakdown of an oxide 30 nanometer thick between a niobium film and indium tin alloy film at 3 values of limiting resistance 100 kilo ohm, 10 kilo ohm, and 1 kilo ohm. As you can see, as high as the limiting resistance, the higher values of resistance of bridge can be obtained. If we used limiting resistance 1 kilo ohm, the minimal resistance of bridge can be obtained about 3-4 ohm, and pure value of bridge resistance about 1 ohm. The resistance formed during the breakdown of metal bridges between metal electrodes arises under the action of a strong electric field, more than 1 million volts on centimeter, in the dielectric as a result of emission of electrons from the cathode to the anode. The emission caused the formation of electron avalanche in narrow channel between the electrodes with a current density of more than 1 million ampere on square centimeter, which caused the destruction of dielectric and melting of the electrodes. First of all, this happens with the electrode having the lowest melting point. In our case, this is an alloy film electrode. During this fast process, the electrode metal enters the breakdown channel, cools to solidification, and forms a metal bridge of the cathode material with possible inclusion of the dielectric material. We calculated dependencies of the resistance of the bridges on diameter of the bridge A and the ratio of the temperature coefficients of the resistivity on the basis of formula 3. We can see from the graphs that at the thickness of the niobium oxide 30 nanometer and these parameters, the bridge diameter is 25 nanometer. Also, we estimate coherence length for the bridge at temperature 2 Kelvin, and this value equal 20 nanometer. And according to the Aslamazov-Larkin formula for short bridge with resistance 1 ohm, we estimate the critical current at 0 Kelvin that equal about 1 milliampere. On next stage, we used the combined method of breakdown of niobium oxide. The electrical circuit presented in Fig 6, and the main element of this circuit is capacitor. The parameters presented here of this circuit, and by this method we can obtain bridge resistance in range from 1 to 8.5 ohm. That corresponds to decrease in the Josephson bridge diameter from 25 to 14 nanometer. Fig 7 presents dependencies of bridge resistance on limiting resistance R sub 2 and dependencies of critical current on limiting resistance. As can be seen in Fig 7, the critical current at 0 Kelvin decreases from 1 milliampere to 0.13 milliampere. On next stage, we prepared superconducting interferometer. Fig 8 presents photo of the structure. We have 3 interferometers. One of them was investigated in the Curriculum Institute of Metal Physics because liquid helium in our institute is absent from 2021. Fig 9 presents family of current voltage characteristics of Josephson film junction fabricated by electrical breakdown of dielectric nanolayer. We can see at temperature 4.2 Kelvin the critical current of the interferometer is about 1 milliampere. The obtained critical current value at this temperature is close to the known theoretical value for short Josephson bridge. Conclusions. It was found that with smooth increased voltage on the electrodes, breakdown occurs at voltage of 12-13 volts, which is practically independent of the size and material of the cathode. The strength of the electric field that is about 3 million volts on centimeter and is determined by the thickness of and dielectric properties of the oxide. The coherence length of nanobridge made of alloy indium and tin was calculated at temperature 2 Kelvin. It turned out to be close to the nanobridge length. This allows us to assume that in superconducting state, a nanobridge with resistance of 1 ohm must have Josephson properties. A superconducting interferometer was manufactured in our institute, but our institute has not produced liquid helium since June 2021. For this reason, preliminary cryogenic measurements were carried out at the Institute for Metal Physics. The obtained critical current value of Josephson film junction at temperature of 4.2 Kelvin is close to the known theoretical value for short Josephson bridge. Thank you for your attention.
Thank you, Dr. Tavera. So now we have time for questions. We have no questions. Thank you again. And now we return back to Professor Eugen lab. Professor Eugen left. Are you with us?
Can you see the full screen?
Now we see your presentation. Please take the floor.
Mhm. Full screen you see.
Yes, on full screen mode.
I'm pleased to present our work devoted to new quantum materials based on functionalized graphene nanostructures. Monolayer, bilayer, and multilayer graphene, as well as various functionalized systems based on it, have been studied theoretically and experimentally for over 25 years. It would seem that nothing new could be discovered in this field. However, in this report, we will attempt to demonstrate that this impression is incorrect. Despite the fact that the effects of graphene intercalating and forming of various functional groups on its surface have been studied for a long time, the change in the electronic structure and the influence of these factors have not been sufficiently investigated. By filling in these gaps, we discovered surprising features of the electronic structure of graphene functionalized with polar oxygen cesium complexes. Namely, the presence of one-hole singularities near the Fermi level in its spectrum, as well as the unusual structure of these complexes themselves, which demonstrate covalent bonds with graphene and formation of superstructures on its surface. In addition, we demonstrated that bilayer graphene with a surface functionalized in this way is the simplest quantum material with both the above-mentioned one-hole singularities and Dirac cones, which can be tuned by intercalating various atoms into the interlayer space. Such systems also exhibit a record low electron work function, which can also be tuned over a wide range of values. Thus, our variant of functionalized bilayer graphene is an ideal platform for exploring advanced electronic phases, such as charge or spin ordering, high temperature superconductivity, and their interplay with topological states. These systems are also promising materials for energy and electronic applications. Ab initio DFT calculations were performed as using the WASP and Quantum Espresso software packages to study the structure and electronic properties of nanostructures based on monolayer and bilayer graphenes with and without atomic complexes, including alkali metals and oxygen. Calculations were carried out using PBE and PBE-SOL functionals, dipole compensations, and van der Waals corrections. Relaxation was applied to our structure. In nature, there are two types of bilayer graphene, AB and AA, which differ in the relative arrangement of graphene layers. The AB type is more stable in nature. The first graphs shows the value of potential averaged along the axis perpendicular to the graphene planes, and its value at the cell boundary can be considered as the vacuum energy level. The difference between this value and the Fermi energy determines the work function of the system. In the case of AB graphene, it is 4.33 electron volts, which correlates well with the experimental data. Both types of bilayer graphene have the electronic structure with Dirac-like peculiarities, which marked as DC on the figures. With an increase in the concentration of the intercalated cesium, the binding energy of AA graphene increases in comparison with AB1, which demonstrate the effect of stabilization of AA graphene during its intercalation. Another effect of intercalation is the shift of the Fermi level relative to Dirac point. The sign and magnitude of this shift depend on the concentration and valence of the intercalant. The formation of polar oxygen-cesium complexes on the surface of monolayer graphene reduces the work function of this system to an extremely low value of 1.03 electron volts due to mechanisms to surface electric dipole moments formation. Instead, Dirac points extended one-half singularity. They're marked on figure as VHS, appear in the electronic band structure near the Fermi level when oxygen-cesium superstructure is formed on the graphene surface. In addition, a covalent bond may form between oxygen-cesium complex and graphene layer. The real Fermi surface of this nanostructure exhibits 6 zones of nesting, which can lead to instability of charge or spin density waves and high susceptibility of this two-dimensional quantum system to such excitations. The schematic type binding model band structure with one-half singularity and Fermi surface with nesting zones of such system are shown here. All above mentioned peculiarities of electronic structure make these new materials an exciting platform to study the interplay of different orders in two-dimensional quantum systems. In the case of bilayer graphene systems with oxygen-cesium complexes, both peculiarities, Dirac cones, and one-half singularities are observed simultaneously near the Fermi level. Additionally, the bilayer graphene can be intercalated with various types of atoms. In our case, with cesium and chlorine, which leads to controlled shift in the position of the one-half singularities and the Dirac cones relative to the Fermi level. Thus, the bilayer graphene functionalized with oxygen-cesium complexes is the simplest and most effective two-dimensional quantum system with tunable both the work function from 1.06 electron volts and the Dirac-Konnes and Van Hove singularities positions relative to the Fermi level due to intercalation with different types of atoms. I presented my conclusions during the report, so I will skip them now. However, I would like to highlight that we discovered a new class of two-dimensional quantum materials based on graphene functionalized with oxygen alkali metals complexes. These materials have a well-tunable structure and electronic properties, and they have the potential to realize different types of orders and their interactions. This theoretical study was carried out in close collaboration between scientists from Institute for Metal Physics, Kyiv Academic University, and University of Zurich. Unfortunately, today I do not have time to discuss our experimental research on this topic, but this could be the subject of a future presentation. Thank you.
Thank you for the Professor for interesting report. And now we will time for discussion. Yes, we have one question.
Thank you for your presentation. I have a question. Why exactly cesium atoms were chosen for intercalation? Why not other alkali metals?
Thank you for your question. We presented cesium, but we calculate all spectrum of alkali metals. And for intercalations and for complexes or with oxygen on the surface of graphene. That results we will publish it in journal.
Okay.
Thank you. Move forward. It will be Dr. Yuri Seroshkin from Lashkarev Institute of Semiconductor Physics of the National Academy of Sciences of Ukraine.
problem of reduction in this community and it's just for my currently there are several methods of optical and nuclear acoustic and internet. Each of them is effective under certain conditions, depending on the type of mind, exposure behavior, and so on. In recent years, new methods, more introduction, including plastic and other individuals. One of them is the laser emitter, which the method that provides a high ability of detection in lower temperature. In this work, we describe the laser acoustic method of manufacturing consists of in execution, vibration, and around seismic waves when irradiated with acoustic waves in the frequency range from 50 Hz till 1 kHz. And measure the vibration characteristics of the soil surface in several points using a remote sensor. For example, the frequency shift of the field reflected from vibration surface is an using study speaking the acoustics of the speaker component of the intermediate frequency signal. The interaction that the object in the soil with seismic waves passes it with light. An object in the soil is detected by high amplitude of surface radiation above this. This slide demonstrates an example of application of this acoustic method or detector by this is a laser multi-pin differential sensor that provides measurement of object vibration intensity sensitivity. It is proposed by the American National Center for Physical Acoustics, one of the leaders in the creation of acoustic sensing. The ability of the complex to detect binary objects was demonstrated by also in field experiments. It was our laboratory experimental center. Composed also loudspeaker, a single open laser vibrator, and containers with different types of soil. The acoustic wave white voice delivered loudspeaker was used for execution, vibration in the soil, providing acoustic level and the soil surface
is up to 100 decibel in the frequency band of 50 to 1000 hertz. The parameter used electron is this it is this slide shows field test of complex. Now, a few words about the method of measurement prediction. The process of the measurement was related. This slide demonstrates scheme of the complex. This is a license report. This is a load speaker. Expose the device. Also a sensor. This computer is used for control of hardware of electricity. This computer is for production process. Also about the basic measure efficiency. Procedure of the both the first step is report the spectrum of signal one photo detected with the type of test photon of digital data. The second is the apply of the data form abused with recording information and the low frequency reflection. This procedure is the receiver signal is universal. As an example, this slide shows a graph of the surface excitation and inhibits in the undefined this method for measuring anxiety of frequencies evaluation is given in better details. First of all, we studied the creation of the surface of field executed by instruments. This slide presents time differences of vibration amplitude in the vibration spectrum of the surface of large volume and the action of this field, the noise of the scale, and the frequency range is from 50 to 1. In the vibration spectrum, I observed First of all, we studied the liberation of surface of executed by the news. This slide presents independence of liberation and liberation statement of the surface of legal as an action. This is this in time with this and frequency of energy. Kilograms. Individual story. So to hertz with amplitude 20 minutes. This slide this slide shows independence of the person spirit. Yes, the action is so resonance frequencies with different amplitudes. Going among the soil, and the additional spectrum, the soil of is a superposition with the vibration of the different parts of the this is slide with questions from interpreting and objective between the spectrum. The slide shows slide shows the spectrum shows three well-defined resemblance. Observer. Is also is mind and also was a center. It's and if always a good point, in the relation to the minister of the then to be observation and also it's a good story for the relation resonance, but so when not only complicated the identification of the relation, but also complicated the intention. I think from if it's necessary to of it and specific frequencies, we can get in the free stream. This result obtained the result obtained us before the aspects of the in proposal taking of fix Yeah, relatively, very the discussion of the problem of yes, limits and yes, balance really far this problem in a significant influence on the progress of work in just
Thank you for your presentation. Now we have time for one small question, if any. We have no questions. Thank you again for your interesting presentation. And the next speaker, PhD student in Jan Smith from Lviv Polytechnical National University. The question phenomena of the structures. For the crystal and silicon device conductors, it's usually used as a part of the structure with the isolation of the crystal layer, whereas the active element of devices are separated from semiconductor subscribed layer below the such a structure is called silicon slate semiconductor slate same way. The results of studies of the skills will make it possible to understand the mechanism of current flow in such a structure. To identify the features of changes in electrophysical characteristics of the material, and this in turn will open the possibility of using micro and other system devices. The aim of this work is to analyze experimental result of the investigation of polysilicon films in semi structures in a wide temperature range from 4.2 kelvins to 300 kelvins up, and including the liquid or heavy metal temperature under the influence of a strong magnetic field up to 15 pascal, with a concentration of boron impurity in the vicinity of metal, the electric transition in silicon 5 on 10 and 15 degrees minus 3. This work we have studied polycrystalline silicon films in similar structures at pre-organic temperature in a strong magnetic field up to 15 Tesla. The assembly structure were a complex structure, a schematic representation, you can see it in the slide. Varies one silicon wafer 40 with orientation 100.2 layer of thermal CO2 or silicon
of symmetry, which was film 3 of C3 and 4 forms the instrument by 3 film of C3 and 4 part of the insulation together with 2. 4 it's a layer of polyc. 5 it's a window in CO2 layer. 6 there is a contact for contact sheets to the wafers with the CO2 layer. 7 and 8 combined observation combined of C3 and 4 and CO2 fields. And 9 elements of their anti-reflection combined of C3 and 4. And 10 it's the direction of scanning and the action of laser beam. Also, you can see the micro photo of some OI structure. Polysilicon films were used to accommodate the active elements of the devices. It was obtained by deposition in a low pressure reactor using chemical transfer reaction method or FCVT. To redistribute and activate the boron impurity and improve the morphology and structure of films, a special method of local heating was used. The crystallization was achieved using a full solid state laser at a wavelength 1.06 micrometers. The developing that structure was designed to study fall effect in the structure. According to the topology shown, the resistance of the polysilicon through and across current flow in the samples was studied in relation to the direction of laser crystallization. For the study samples of similar structure with the boron impurity concentration corresponding to metal dielectric transition in silicon with a concentration 5 on 10 in 18 centimeter at -3 degree were used according to coefficient measurement sample with boron impurity with the concentration 2.4 on 10 in 10 degree and 3.9 in 10 and 19 degrees centimeter -3 degree. For crystallization and samples with concentration on impurity 4.8 on 10 and 18 degree and 1.7 in 10 and on 12 degree after crystallization were selected. The low temperature studies of some ice structure have been carried out in temperature range 4.2 to 300 Kelvin and magnetic field up to 15 Tesla. The measurements of sample resistance and prevailing temperature can be held in international laboratory of magnetic field and low temperature in what we could see the crystal. The samples have been cooled up to 4.2 Kelvins in a halogen. Also, you can see a picture and much photo of not recrystallized polysilicon layer and recrystallized polysilicon line.
Despite the previous studies investigated a negative magnetic resistance posed by a jump in conductivity at low temperatures. The main attention of this work was focused on the study of polysilicon with a concentration of impurity 3.9 on then in 10 degrees centimeter minus 3 degree. As you can see in the first figure, the absolute value of magnetic resistance in this film increase linear in temperature magnetic field range from 1 to 13 Tesla and reaches 7% without saturation. In the range less than 1 Tesla, there is a presence of positive magnetic resistance according to the models in proposed. And in this on slide, we can estimate the contribution of paramagnetic centers with spin magnetic moments. For heavily doped semi structure with charge carriers concentration 1.7 from 10 in 12 degree and temperature 4.2. It's a crystallized polysilicon. You can see that magnetic resistance reach only 1%, and there is absence of any anomalous magnetic resistance. The features of the behavior of anomalous magnetic resistance of polyC in semi structures with a concentration boron impurity 3.9 on 10 in 19 degree and 2.4 on 10 in 18 degree. You can see on a quadratic and logarithmic scale. Magnetic field range less than 1 Tesla. It's a result of comprehensive study of the magnetic resistance of polysilicon films in semi structure with a boron charge. There is concentration 3.9 on 10 in 19 degree before laser crystallization with a fine grain structure are characterized by linear without saturation. Without saturation from 1 to 14 Pascal. Due to influence of a significant number of intergranular boundaries, which are considered to be the structural defects in paramagnetic centers with the spin magnetic moments, the magnetotransport properties of samples with concentration of impurity 2.4 on 10 and 18 degree show a negative magnetic resistance at temperature 4.2 to 30 kelvins in magnetic field up to 15 Tesla within the framework of jump conductivity. On the contrary, the policy was a concentration of impurity of 3.9 on 10 in 19 degree, and anomalous positive magnetic resistance was found. It's characterized by a jump in magnetic resistance at low magnetic field less than 1 Tesla. It's related to the contribution of paramagnetic centers with the spin magnetic.
Thank you for your question.
Thank you for your presentation. One small question.
What fraction of the silicon you use for your board? Maybe so, for some, silicon.
Thank you. Thank you for the question, and thank you again for your presentation. We move to the next session, nanostructured surfaces, and the first speaker in this session, Dr. Valentin Volobuyev from International Research Center, Marktop Institute of Physics, Polish Academy of Sciences, and National Technical University, Kharkiv Polytechnical Institute. We see your presentation. You can start your report.
Okay, great. Okay. First of all, I would like to thank organizers for the opportunity to speak this conference, and as well sponsors for doing research in this direction. So basically, what I'm going to talk is Rashba effect on the surface of IV6 semiconductor, which is caused by submonolayer deposition. And I basically present angle resolved photoemission results. So to briefly remind you, to briefly remind you about the Rashba effect, it actually was predicted by our famous physicist whose life was related strongly to Ukraine. So he works in Kiev Institute of Physics, and unfortunately he's passed away this year. So basically, this effect is removing spin degeneracy from the electron or hole bands in solid state, and this is only it can be observed in material with strong spin orbit coupling, and where the inversion symmetry is broken. So one of these, it's definitely surfaces or interfaces at the heterostructures of the films, and it was I guess first discovered in this gallium arsenide, aluminium gallium arsenide quantum well structures. So basically, the important characteristic of this effect is so-called this Rashba constant, which is proportional electric field. So basically, you need a gradient of the electric field in the direction perpendicular to your structure, and as well, like it should be small to have this big alpha coefficient. You need small effective mass, and it can be observed in the narrow band semiconductors. So basically, where this effect is utilized, it's so-called Rashba-Edelstein effect, where you have adjacent ferromagnet, so you can due to this spin momentum locking, you can divide the spins in your semiconductor. So for this reason, we study IV6 semiconductor. It's from FOS and it's basically lead, tin, germanium chalcogenides, and they have simple rock salt cubic structure. So this 1-1-1 surface is polar. Therefore, we can naturally introduce this electric field effect at the surface. Unfortunately, these materials they cannot be prepared simple cleavage. So we wanted to study RPS in these films, and this material cannot be prepared by simple cleavage. Therefore, we can grow these materials by MB, in form of thin films. On this barium fluoride substrate, we use such compound sources. And that's our MBE setup. So several words about structure. So it is important for the photo emission investigation, the smooth surface, and we definitely study the surface for the this lead tin selenite or lead tin telluride compounds, and one can see that it is atomically smooth surface. It's also confirmed by Reed. We can determine easily the tin content if we allow it. So basically, there is it goes according to the Weger law, definitely strains and so on. As I said, the surface is important. Therefore, for such measurements, we have to protect the surface of our films. So one way is to use such a ultra-high vacuum suitcase, which is attached to the MB, and then we go to the synchrotron, and you can observe this suitcase attached to the Uranus beam station in Krakow. Alternatively, we can deposit in our MB such material as selenium and simply decap it as well in the at the synchrotron. At the synchrotron, there are possibility to deposit some metals, some materials in situ that can be as well done. And several words about deposition. As you can see, for example, here we deposit the transition metal manganese, and that's nicely streaky ring pattern. And if we deposit small amount in this is 0.8 angstroms, so one can see that nothing happened. Only this, so the streaky pattern is still visible, but there is like strong background, and this is most probably concerned due to amorphous film which is present on the surface. So, and just maybe not all of you knows about this techniques, which is angle resolve photo emission spectroscopy. I just wanted to briefly remind, very brief. So basically, we illuminate our samples with photons. It's usually a soft X-ray. In this case, it's exactly soft X-ray, and they emit photoelectrons. It's external photo effect. And because the momentum and energy conserved for the electron which removed from solid, they have basically similar kinetic energy and momentum. So therefore, they go to this hemispherical analyzer, which is basically capacitor, and they are separated according to their kinetic energy and angle, and then we can recalculate this kinetic energy to the binding energy and angle to the k vector. So basically, finally, we have our results. That's what happens if we deposit a small amount of tin on the surface of lead selenide, and as one can see, that we have p-type. That's the band structure. Basically, that should be conduction band, but we cannot see it because the Fermi energy in the gap. And we start to deposit tin, and you can see appearance of conduction band. And this conduction band becomes splitting, so we basically observe this Rashba effect. As well, we can see the presence of this quantum well level. It's not here very well seen, but definitely, for example, that's lead telluride, and we deposit lead on it. One can see such a nice Rashba spectrum with a quantum well level, and this is why it's associated with such formation of such asymmetric quantum well at the surface. So so our materials, as I said, if we mix lead telluride or tin telluride with tin, it's happening so-called band inversion, that your band they swap their place in energy. This is result in a class of material called topological crystalline insulator. It's a little bit different from usual Z2, like this bismuth calcagenide compound, because it's protected not by time reversal symmetry, by crystal symmetry of 1-0-0 plane. And you on surfaces like 1-1-1, you can observe such surface states, Dirac cones. So basically, we work mainly in gamma, and that's our results. So one can see. So this is for different sample, which has for each sample we deposit 0.61 layer of tin on this lead tin selenide, and one can see, and each sample have different tin content, so we can see that how the gap is closing. So and this formation of topological surface states. And in opposite, if we take 25%, we again observe formation this Rashba state. So the question is it like previously we only use like lead and tin, but for example, if we deposit some other metal, especially transition one, which can bring magnetism to our system, what happened? So basically, as answer is here, it's basically the same. So we can see again formation of this additional bands, Rashba splitted bands, formation of the quantum well levels. So, and basically our measurement shows that we have both combined Dirac and Rashba spectrum for in such way that inner branches of Rashba, they coincide, they might be hybridized with surface states of our topological insulator. So this results, it's quite unusual and interesting, and basically it can be utilized. It's actually already proven that, and what people say that one should expect, that this characteristic of spin charge conversion in spin charge conversion devices, when you have this magnetic layer, can be improved, but it's definitely depends on how the spin texture, how this moments of this electron, how oriented with respect to each other. So another stuff, another possibility, another application is because lead and tin, it's a superconducting metal, and basically it's can be made such kind of nanowires, and this can be used for like Majorana-based qubits. This Rashba, it's important ingredient for such wires, and we have currently a project on this. So the idea to fabricate this for 6S device, such a device with nanowire, and combine it into heterostructure as well with superconducting metals, and basically we have opportunity for right now for 1.5 years for training. So if young scientists, some people who have master degree would like to participate, you're welcome. Just write me email. So and finally the conclusion, it's that we observe interesting effect, we observe interesting spectra, so-called Dirac-Rashba, and this Rashba splitting is quite large. It's correspond to other system with such a giant Rashba coefficient, and its cost, we show that it costs by deposition of various metal, and as you can see, there are many systems, and this effect is robust. Thank you very much for your attention.
Thank you for the presentation. Good question. We have no questions. Thank you again for the interesting presentation. According our program, next speaker must be Professor Oksana Poplak from University of Milano, Italy. But as I know, she cannot provide your presentation, and we move to the next speaker, Dr. Vitaly Bilanich from Uzhhorod National University from Ukraine.
Good afternoon. My report is under the title Mechanism of Nanostructuring of Chalcogenide Films under Electron Irradiation. This talk presents the results of studies of the interaction of chalcogenide films with an electron microscope beam and the formation of surface relief under localized electron irradiation. The model of mechanism of electron-induced phenomena is amorphous semiconductor films are also presented. The research was carried out within collaboration between Uzhhorod National University and Pavel Joseph Shafarek University and Koshice, and for Ukraine researchers, these scientific researchers were partially funded under project of the Ukraine Science and Technology Center, and the work of Slovak scientists was partially funded by the project of the Slovak Research and Development Agency and grant next generation through the Recovery on Resilience Plan for Slovak. Chalcogenide glasses and film are not crystalline semiconductors materials based on the sulfur, selenium, and tellurium. And these materials have application in various infrared technologies, infrared optics, optical lithography, holography, and information security. Chalcogenide glasses based on sulfur, selenium, and tellurium are transparent in the wavelength range of more than 11 micrometer for sulfides, 15 nanometer for selenides, and 20 nanometer for tellurides. Chalcogenide materials are used as photosensitivity elements in very devices. In chalcogenide films are used to record information on optical media to manufacture planar, waveguide switches, micro lenses, holograms, and in the photolithography. For our studies of electron-induced phenomena, chalcogenide films of germanium, selenium, arsenicum, selenium, and arsenicum sulfur systems were used. These films we obtained by resistive thermal evaporation in vacuum or bulk chalcogenide glasses of sapphire substrates. The thickness on this film measured by the interferometric method was 4 micrometer. The film have been point-wise irradiation with using TESCAN scanning electron microscope model Vega with parameter accelerating voltage 30 kilovolt, cross section spot size of electron beam is equal 640 nanometer, and the electron beam current 60 nanoampere. We performed irradiation at exposure time from 10 microsecond to 5 second, the point dose of electron beam irradiation. The film surface and surface potential in the irradiation region were investigated using scanning probe microscopy, Bruker model icon, the Kelvin probe force microscopy measurements were performed at ambient condition. For exposure time for 10 microsecond to 5 seconds, 20 different radiation doses were selected, which were uniformly distributed or this range on a logarithmic scale. For each irradiation dose, arrays of irradiation point measuring 20 by 20 were formed on this surface of these chalcogenide films. Distance between the centers of irradiation areas was 10 nanometers, and as can be seen from figure 4, and the irradiation time of 0.3 millisecond per point, a protrusion is formed on the film surface. And if irradiation time is 1.9 second per point, on the chalcogenide surface film formed craters with depths 300 nanometers. Figure 5 shows the dynamic of surface relief formations in chalcogenide films on the arsenicum sulfur and germanium selenium systems under different electron beam irradiation times. The irradiation of various chalcogenide films with an electron beam leads to nanoscale surface structuring. Surface relief analysis has shown that the pattern of electron-induced structuring are similar of chalcogenide films of different compositions. The applied irradiation range can be divided into several intervals. The first interval, this is low radiation dose. Third dose intervals is high irradiation dose and middle dose. In this interval formed combined relief with depression of centers of coneous Gaussian cross sections. The figure 6 shows that regardless of chemical composition, chalcogenide films exhibit identical trends in the evolution of surface relief. These depend on the irradiation dose. Electron beam exposure can lead to the formation of several different types of surface relief in chalcogenide films. Gaussian cones, structures with an axial cross-section corresponding to Gaussian cover. Gaussian-shaped depressions centers along the electron beam axis. Taylor cone is formed in some films, cones with an asymptotically sharp axial profile. And the combined reliefs, one or two cones located at the edge of depressions. Figure 7 shows that in the arsenicum-20 sulfur-80 film at a Taylor cone height of 4 micrometer height. And it can be seen for this figure on surface on the film for Taylor cone or depression with Gaussian profile. Surface potential in the irradiation region of the chalcogenide films were investigated using a scanning probe microscopy, platinum iridium type, were used for the surface potential mapping by Kelvin probe force microscopy. These measurements were performed in a frequently modulated mode at ambient conditions. For different films, the surface potential in the irradiation areas varied from 5 millivolt to 120 millivolt. Figure 8 showed KPFM scans of the surface relief potential on the irradiation areas of chalcogenide films, germanium 15, selenium 85. It can be seen from this figure formed Gaussian cone on the surface on this film, and if irradiation time is equal 50 millisecond on the surface on this film form Taylor cone, and surface potential is equal 40 millivolt. The following regularities of electron-induced effects are observed in the chalcogenide films. Under the action on the electron beams, mass transport occurs in the films, leading to surface nanostructuring at the formation of surface relief of various shapes. As a result of a detailed study of these electron-induced processes in amorphous fields, we have established them following. In amorphous chalcogenide fields of different systems, electron-induced processes have a charge-driven mechanism. The nanostructure of the surface of chalcogenide films under electron beam exposure is determined by electrostatic interaction in the space charge region. The formation of the space charge region depends on the parameters of electron irradiation as well as on the structural and physical properties of the chalcogenide film. The key structural properties are the presence of a specific type of defects of the film's chalcogen atoms with dangling bonds. The key physical properties are the electrophysical characteristics on the film, electrical conductivity, and charge carrier diffusion coefficient. The shape and parameters of the space charge region depend on the chemical composition of the film, the density, and the value of the first ionization potential, as well as on the energy of primary electrons. And the space charge region has a bilayer structure. To understand the mechanism of interaction of amorphous chalcogenide films with an electron beam, a model of electron-induced processes was developed. The model parameters were calculated based on the initial data of the physical properties of the films and the parameters of electron irradiation. When an electron beams on the simple falls on the simple surface, thermalization of the inside electrons occur due to both elastic and inelastic scattering in a limited region. For chalcogenide films at a primary electron energy 30 kilo electron volts, the interaction region has a spherical shape. The size of this region is determined by the penetration depth of the primary electrons into film. For chalcogenide films, this parameter was calculated using Kanayo-Kayama formula. Figure 10 shows a schematic diagram charge model of the space charge region formed during interaction of primary electron beam with chalcogenide film. The backscattering electron depth was calculated using formula 2 on the chalcogenide glass of germanium selenium system. This parameter is equal from 4.6 to 4.2 nanometer. Depth of backscattering electron yield was calculated by formula 3, and this parameter changed for these chalcogenide films from 1.3 to 1.4 micrometer. This parameter see from figure 10. The spatial distribution of charge density in the interaction region with the Gaussian distribution of electrons in the electron microscope beam was calculated and calculated by formula form. and internal field in the interaction region was calculated using formula 5. The charge density decreased from the maximum value to 0 when moving away from the centers of space charge region. High density positive charge is formed in the space charge region near the surface in the region of low irradiation dose. This is first dose interval. The negative charge deep in the film and its bulk density are very small. The total electric field strength is maximum at the edge of positive charge region. Conclusion. Electron radiation of chalcogenide film causes charge accumulation in the irradiation region. This leads to the formation of surface relief and the appearance of surface potential. Cone-shaped reliefs carry a positive potential, while crater-like relief carry a negative one. When charge density and electric field reach critical values, sharp tail cones form. And this point, the shape charge region collapses and the excess charge is emitted through the cone type. Thanks for your attention.
Thank you for your presentation. We have time for question. We have no question in conference call and in Zoom, no question. Thank you again for your presentation. The next speaker, PhD student Alexei Imenko from National Technical University, Ukraine University Technical Institute. Alexei, are you with us? I don't see Alexei in Zoom. Maybe we return Alexei later. According to programs, the next speaker must be PhD student Ruslan Krivoshabka, but as I know he has an electricity and cannot our conference and we moved. Next speaker at National University, Anatoly, are you with us?
Доброго дня.
Hello.
Доброго дня. Доброго дня, шановні колеги.
Our European language is English.
Ну, я приготовив презентацію на українській мові. Зрозумів так, що це можливо на українській, можливо на англійській мові. Ну, якщо ні, то можу приготовити постер тоді.
Це ви англійською доповідати?
Ну, англійською не готовий доповідати.
Добре, тоді давайте. Да.
Можемо
Так, можете розпочати, але можете ви зробити доповідь, презентацію на повний екран?
Так. Так, є? Алло?
Спочатку ви припиніть транслювати екран.
Мене
Потім
видно?
в Zoom закрити трансляцію екрану, потім зробити в повному режимі презентацію і потім розшарити вже вікно з повним презентацією в повному екранному режимі.
Видно? Мене видно?
Видно, але все ж таки не в повному екранному режимі. Давайте розпочнемо.
Мене чути? Чути мене?
Так, вас чути.
А презентація на повний екран?
Не на повне, але давайте розпочнемо. Так, воно видно.
Добре. Значить, доброго дня, шановні колеги, шановні гості. Темою моєї наукової роботи було дослідження спектрів електрон-фотонної емісії поверхонь ЛГК кристалів натрій-хлор і калій-хлор, модифікованих наноплівками та наночастинками міді і срібла. Значить, актуальність. Наночастинки та наноплівки металів, що диспреговані в матриці діелектричних речовин або напилені на їхній поверхні, демонструють особливі оптичні і електричні властивості. Зокрема, здатність металевих наночастинок і наноплівок підсилювати локальні поля поблизу їх поверхні. Дає підставу розраховувати на їх різноманітні застосування. Це дозволяє їх використовувати при розробці нових сенсорів, оптоелектроніці, нелінійній оптиці, молекулярній електроніці для зберігання енергії тощо. Значить, мета дослідження. Методом електрон-фотонної спектроскопії дослідити емісійні та люмінесцентні характеристики поверхні наноструктури.
Я вибачаюсь, але у вас слайди не вимикаються.
Угу.
Нема.
Так.
Вам придеться, так як у вас не повний режим, у вас автоматично слайди не переключають. Вам треба весь час збоку, бачите, там 1, 2, 3, 4 вручну переходити і нажимати відкритий, цей повний режим. Тому що у вас презентація не в повному режимі. Ну так, да. І так для кожного слайду. Все, у вас зараз повний режим. Все, супер.
Да, мета дослідження. Значить, методом електрон-фотонної спектроскопії дослідити емісійні та люмінесцентні характеристики поверхні наступних виготовлених експериментальних зразків. Значить, чистих поверхні лужно-галоїдних кристалів натрій, хлор і калій, хлор, поверхні кристалів натрій, хлор і калій, хлор, що модифіковані гліцерином, поверхні кристалів натрій, хлор і калій, хлор, наноструктурованих наночастинками срібла та міді, зрощенів срібла і гліцерина, міді та гліцерина, тобто методом осадження наночастинок зрощену на поверхні кристалів. Значить, і поверхня кристалів натрій-хлор і калій-хлор модифікованих наноплівками срібла і міді. Метод термічного напилення та метод перенапруженого наносекундного високовольтного розряду. Записати та розшифрувати спектри електрон-фотонної емісії поверхнень виготовлених зразків, встановити природу випромінювачів та зробити значить, записати та розшифрувати спектр електрон-фотонної емісії поверхні виготовлених зразків, встановити природу випромінювачів та зробити висновки про чутливість методу. Загальна схема установки. Бачимо на малюнку, значить, дослідження спектральних характеристик електрон-фотонної емісії поверхні кристалів проведено в оптичному інтервалі від 2000 до 8000 ангстрем на надвисоковакуумній установці УСУ-4 методом електрон-фотонної спектроскопії. Значить, основним робочим насосом є магніторозрядний HMD0401 Норд та сублімаційний насос. Магніторозрядний насос здатний створити в об'ємі камери розрідження 5 на 10 в мінус 9 тор. Сублімаційний насос вмикається після досягнення в камері розрідження 2 на 10 мінус 8 тор і здатний створити міні-вакуум до 2 на 10 мінус 10 тора. Значить, умови експерименту. Значить, схема електронної гармати бачимо на малюнку. Основні параметри електронної гармати. Прискорюючий потенціал від 0 до 1000 електрон-вольт, нагрів катода від 0 до 12 вольт, струм пучка від 0 до 5 мА, густина струму від 0 до 160 мА на сантиметр квадратний, діаметр пучка від 2 до 5 мм. Підготовка зразків досліджень до експерименту. В якості заготовки для мішені використовується масивний монокристал натрій хлор з високими трансляційними властивостями. На першому етапі з одного сколу цього кристалу готувалося декілька одинакових мішеней з наступними лінійними розмірами 12 на 6 на 3 мм. Наступним етапом виготовлення зразків була модифікація сріблом поверхні інших зразків. Наноструктурування здійснювалося методом осаду концентрованого колоїдного розчину срібла в ліцерині на поверхні монокристалу хлористого натрію. Значить, концентрований колоїдний розчин наносрібла в гліцерині, срібний щит, його так називають, було одержано в Інституті надтвердих матеріалів НАН України. Концентрація наночастинок срібла в розчині складає не менше 100 мг на літр. Масовий відсоток срібла в гліцерині 0,01%. Розміри частинок срібла від 10 до 80 нанометрів. Виготовлення інших зразків відбувалося таким же методом. Краплю гліцерину рівномірно наноситься на поверхню сколу монокристалу натрій хлор і висушувалося переродньо в протязі тижня. Оцінка якості поверхні монокристалу натрій хлор до і після наноструктурування та модифікації було здійснено за допомогою електронного мікроскопу. Виготовлення зразків методом напилення. Напилення наноплівок срібла на поверхні монокристалів натрій хлор і калій хлор здійснюється класичним методом термічного напилення в заводській установці вакуумний універсальний пост ВУП. Тиск в камері для напилення 10-4 до 10-5 тор. Температура розігріву срібла 1100 градусів Цельсія. Виміри товщини напиленого шару срібла та міді. Виміри проводилися еліпсометричним методом на спеціальній установці ЛЕФ-3М. Цей метод вимірювання потребує знання наступних параметрів досліджуваного зразка. Коефіцієнт заломлення поверхні підкладки, на якій проводиться напилення, в нашому випадку поверхня монокристалу, також показники заломлення об'єкта напилення. В нашому випадку срібло і мідь. Досліджені сколи поверхні чистого монокристалу натрій хлор на поверхні монокристалу натрій хлор після наноструктурування сріблом. Бачимо чистий натрій хлор, модифікований сріблом і після модифікації гліцерином. Бачимо, що при модифікації гліцерином шорсткість зменшується. Значить, спектр електронфотонної емісії поверхні монокристалу натрій хлор, що зазнав впливу гліцерину, потрібен для того, щоб ми врахували чи включили вплив гліцерину. Ми бачимо, що форма спектру та сама. Хаrakтеристичні лінії ті ж самі атомів натрію в даному випадку, а по інтенсивності він став менший. Це пов'язано з залічуванням, зглажуванням. Природа випромінювання в спектрах електронно-фотонної емісії всіх зразків досліджень може бути наступна. Значить, бачимо спектр чистої поверхні монокристалу натрій-хлор. Тут поверхня монокристалу натрію, що зазнав впливу гліцерину. Бачимо, спектр зменшився. Спектр електрон-фотонної емісії наноструктурованого срібла монокристалу натрій-хлор чистого. І порівняльні спектри досліджуваних зразків. Бачимо, що натрій, хлор, срібло і гліцерин він найбільший, чистий синьою лінією, і з гліцерином спектр нижчий, порівняно з іншими. Порівняння спектр електрон-фотонної емісії натрій, хлор плюс гліцерин, натрій, хлор плюс модифікований сріблом з гліцерином і модифікованим міддю. Бачимо, що найвищий спектр – це натрій, хлор, модифікований гліцерином і сріблом. Спектр електрон-фотонної емісії натрій, хлор і мідь. Напилений зліва спектр і наноструктурований. Спектр електрон-фотонної емісії натрій, хлор і срібло. Зліва напилений, справа наноструктурований. Спектр електронної фотонної емісії калій, хлор і срібло, і калій, хлор і міді. Зліва напилений, справа наноструктурований. Всі спектри досліджених поверхніх разом. І значить, аналіз результатів та висновки. Значить, природа випромінюючих спектрах електронно-фотонної емісії всіх зразків досліджень може бути наступна. Неперервне випромінювання з максимумом біля 500 нанометрів, на нашу думку, є рекомендаційним свідченням, яке виникає внаслідок збудження електрон-діркових пар і наявністю дефектів типу F центрів різної кратності, що зумовлено появою нових модифікованих дефектів типів HA та ВК центрів в об'ємі кристалу. У наноструктурованого сріблом хлористого натрію збільшилася інтенсивність неперервного випромінювання на 20-30%. А у наноструктурованого мідію хлористого натрію інтенсивність неперервного випромінювання збільшилася на 10%. Ми пояснюємо це дефектами типу HA і H' центра і, можливо, плазмонним випромінюванням срібла та міді для поверхні наноструктурованої сріблом. Однак слід зауважити, що аналізуючи спектр електрон-фотонної емісії зразків з напиленими наноплівками на поверхні ЛГК кристалів, наприклад, сріблом, максимум неперервного випромінювання зміщений на 50 нанометрів в довгохвильову область. Ми не можемо обмежитися лише впливом плазмонного випромінювання. В неперервному випромінюванню наявні і інші складові. Зокрема, свій вклад вносить рекомендаційне свідчення, яке виникає внаслідок збудження електрон-діркових пар електронної підсистеми натрій-хлор, фононне випромінювання та утворення нових дефектів заміщення. Головною причиною виникнення дефектів є наявність в атомі припаркованого шару частини розірваних, а отже і ненасичених зв'язків. Тому електрони приповерхневих атомів мають тенденцію утворювати нові зв'язки. Характеристичне випромінювання атомів лугу – це стимульована електронна десорбція з поверхні кристалу атомів лугу у збудженому стані. Результати проведених досліджень вказують, що метод електрон-фотонної спектроскопії чудово реалізується для дослідження наноструктурованих об'єктів та багатокомпонентних матеріалів. Дякую за увагу.
Thank you very much for your interesting talk. Maybe we will have one question. One moment.
Дякую за вашу цікаву доповідь. У мене два питання. Перше, які розміри були наночастинок срібла, ті, які були колой до осадження, а також масова товщина напилених плівок срібла? І друге питання: чи досліджували ви стабільність цих систем, зокрема, чи не окислювалося у вас мідь?
Мідь не окислювалася, вона доставлялася теж з інституту і в спеціальній пробірці вносилося в гліцерин і наносилося на кристали. І воно висушувалося в гліцерині і не окислювалося. Ну, якби да, і товщина плівки перевірялася мікроскопом, електронним мікроскопом, товщина її було 40 нанометрів.
Дякую.
Дякую за доповідь. У мене коротеньке питання. Скажіть, будь ласка, монокристали ви вирощували самостійно, чи все-таки це були комерційні препарати?
Монокристали ми теж брали з інституту. І вони відповідають всім нормах. Потім ми, щоб досліди були більш реалістичними, ми з одного великого кристалу робили сколи. Таким чином.
Дякую. Дякую. А скажіть, будь ласка, наскільки міцно тримається це наноструктуроване світло на поверхні вашого кристалу?
Прекрасно тримається, дуже добре, тому що ми його відправляли і для дослідження шорсткості в університет Кошице і в Київ відправляли, воно прекрасно держиться. І спокійно можливо транспортування, і не треба якихось особливих умов.
Дякую велике. Це було останнє питання. В чаті в нас немає, було два запитання зала. Дякую велике
Вам дякую.
Зараз ми переходимо до завершальної сесії. Це закриття нашої конференції. Dear colleagues, now we are... One moment. Доброго дня. Доброго дня. Переходимо до завершальної сесії. І зараз ми подивимося, як проходила наша конференція. Dear colleagues, now we are moving to the last session, and we together have opportunity to look some photo from our conference. I wanted to mention that our conference was in hybrid format. We had live broadcast of all days of conference. That's why all of you can visit our website of NANO conference and find the video of all days. So you have opportunity to look again and to watch all presentation, and at the end of each presentation you can find contact the information about the process of this presentation, and directly can contact with scientists with whom you potentially can to cooperate in the future. And I invite you to do it because you know that conference is only start. After the conference, as a rule, you return back with some ideas and maybe with new contacts with whom you wanted to cooperate in the future. I invite you to continue to do it. I mean, to implement new idea to build new bridges between you, because
you know that we had quite a lot participants at this year. Despite the war, we totally had about 600 registration form from scientists from different countries and from different regions of not only from different countries of the world, but also from different regions of Ukraine. That's why each of you received the abstract book, where you can also find the corresponding email of each author of abstracts. And I think this year we also will share electronic version of this book, but only for registered participants. Here you can see 3 days of our conference. We had poster session, we had online, on-site participants. Also, we have quite an interesting discussion. If we are speaking about the place where will be the next conference, I think we will do it as we do each year. We will ask you, we will prepare maybe a survey and ask you about 2-3 places where potentially we can organize this conference. But as you know, our conference on annual basis, and I hope that everything will be good next year. Maybe it will be this year, and we will organize more big conference and invite more scientists abroad on site, not only online, but also on site. Thank you for your time. Thank you that you with us, and see you next year.
Українською так буде краще. Ну, я хочу подякувати організаторам цієї конференції. Вона проходить традиційно в наших західних регіонах. Організаторів, але її працездатність, тому що це не так просто. Кожен, хто організовував конференцію, чудово знав. Я теж організую конференцію, я знаю, це не дешево. Тому дуже дякую і команді всі, хлопцям, які працювали, дівчатам, і не дивимося, що на конференції позитивно. Може, в Закарпатті. Дякую.
Thank you for warm words. I only wanted to mention that all photo from conferences, this conference you can find on our social networks. We have Nanotechnology Nanomaterials Facebook page of our conference, and there we have about 1,000 participants, and I invite you to follow us, and there you can find all information and all photo and video and links. As a rule, if we have news, we also post it on this Facebook page. Also, we decided to create a group, maybe in Telegram, and invite everyone from previous 12 years of conference, and it can be very big group. Whereas we also can post it with some information. I think it's possible also to use for cooperation, for looking new partners for new projects, something like that. It's additional information for you. Thank you.